Hello there, everyone. So we will start this session. I'm Andris Sutka, and I'm from Riga, and this will be my pleasure to chair this session this morning. And as a first speaker, I would like to invite Jeremy Martin. So please, Martin, if you are there, please, floor is yours. Thank you.
Thank you for the introduction. Good morning, everyone. So I'm going to share my screen. Okay, so please tell me if you can see my presentation.
Yes, we can see.
Okay, thank you very much. So good morning again. My name is Jérôme Martin, and I'm going to talk this morning about band edge emission enhancement in sputtered zinc oxide thin film with ultraviolet surface lattice resonances. So let me introduce the subject of this topic. So the goal of this research is to study the possible interaction between plasmonic resonances in the ultraviolet invisible or visible, coupled with a semiconductor with a wide band gap, such as zinc oxide, as the title said it. So a few papers in literature, just to see some application. So the coupling between plasmonics and semiconductors can lead to enhanced optoelectronics, for instance, if you can see on the left image of the enhancement of photodetector in the UV, thanks to the absorption of the aluminum particles on the top of the zinc oxide film. The second paper that I want to show you at the right part of the slide is about some more complex aluminum plasmonic structures, which can tune either plasmonic resonance in the visible on the UV, and you can control the emission of the zinc oxide as you can see on the graph. Okay, so the goal of this subject is to study this kind of hybrid structures and to try to go further, as I'm going to show you. So first, let me to speak about the material we are going to use for the plasmonics, which is aluminum. So aluminum is a very good candidate for the plasmonics, I would say, in the blue, violet, and ultraviolet, because it is a metal down to wavelength into the deep UV, roughly in 18 nanometers. You can see, if you look at the permittivities, that it behaves as a metal, so with quite low losses in the spectral region of interest. It oxidizes, but actually this is a passivation, so it forms a 2 nanometer oxide, which is very stable in time. And aluminum is also compatible with CMOS technology and all the semiconductor optoelectronics. So this is a very good candidate. So the only issue I would say is that it has quite high, if you look at its band structure, sorry, you can see that there is interband transition in the near infrared, which is very detrimental, as you can see in the losses of aluminum. So in the visible and infrared, it's a very bad metal compared to gold or silver, but in the ultraviolet, of course, it's one of the better. Okay, so what we are going to study here is this kind of sample. So in the lab, we can sputter zinc oxide thin films on top of a quartz substrate. So it will be the plane, I would say, of emitter, of excitonate emitters. And on the top of this zinc oxide, we are going to couple with aluminum arrays. Okay, which will be electron beam lithographed. So this is lithography with electron beam. Okay, so before starting to show you the samples, I'm going to talk a little bit about the heart of the subject. It's actually to study the difference between what we call the lattice modes and which is actually a collective oscillation of plasmonics arrays but which are coupled with a Rayleigh anomaly or a diffraction order. So why we are going to use that? Because if you just put basically, as you can see on the, as you can see on the first images on the top left, if you just do an array of LSPR, you will have the absorption cross-section will show you resonances corresponding to the plasmonic resonances of the single particle. But if you tune the pitch between the particle to coupled with a Rayleigh anomaly, you will have, as you can see on the left column, the image B, that you can have some very better quality factor due to the coupling of the plasmonic modes and the Rayleigh anomaly. And this mode will allow us to couple better, as I'm going to show you, with the zinc oxide on the bottom, because those modes are more photonic-like because of the standing wave you can see here. So they are going to couple and to have a good spatial overlap. The electric field, the electric field sustained by those hybrid modes has a very better spatial overlap with the underlying zinc oxide layer. So the last image on the bottom right is what we did a couple of years ago with aluminum arrays. You can see a splitting due to the couple of the plasmonic arrays and the Rayleigh anomaly. So you can tune and make the hybrid modes with a better quality factor even in the UV. So what do we expect with shell samples? So you know that zinc oxide has a bond edge and exciton transition in the UV. So this is the middle part of the graph. And when you couple emitters with plasmonic structures, you can basically have two enhancement or control. The first one is the couple mechanism 1 to the left, which is linked to the absorption enhancement. So plasmonic structures act as a pumping enhancers, which is going to excite more efficiently in the near field of the emitters. On the right part, this is the Purcell effect, which is going to enhance the decay rates of the emitters due to the local density of states, which is enhanced in the vicinity of the zinc oxide also. So basically here, as you know, zinc oxide has a UV near bond edge emission gap, but also defects in the visible. So we can play with both of those emission and wavelengths. So that's what we are going to do. So now I'm going to talk a little bit more precisely about the samples we did. So those are arrays of aluminum nanorods. So why nanorods? Because nanorods with the long axis and the short axis will sustain both UV and visible plasmonic resonances for a same sample. And then we are also going to play on the pitch, so the distance between the nano antennas, to make appear surface lattice resonances, so coupled with a Rayleigh anomaly or not. So we can distinguish the SLR and the non-SLR substrates, plasmonic samples. The structure D is simple cylinders with no anisotropy, which will be actually just a reference sample to be sure that our signal is linked to the anisotropy of the nanorods. So basically, the first characterization of those samples will be the absorption in order to unveil the plasmonic properties. So this is this figure. The first row corresponds to calculation. The second row corresponds to experimental absorption measurements, extension, not absorption, extension measurements. And the C is again a calculation to look at the electric field above the zinc oxide layer. So those four structures are tuned to have LSPR or SLR in the UV. For instance, if you look at structure A, we tuned the plasmonic array in order to have an LSPR at a wavelength of 382 nanometer, which is very close to the near bond edge emission of zinc oxide, and the LSPR is tuned at 125 nanometer, which is basically located in the region of you have visible transition due to the defects. Structure B, this is also a nanorod, but as you can see on the curves, this is an hybridized mode. And the hybridized mode in the UV has a very sharp extension peak due to those modes which have a very better quality factor. And if you look at the electric field, you can see those hybridized mode with the first Rayleigh anomaly when you have the electric field at 382 nanometer, which behave like a standing wave due to this hybridization. Structure B is tuned at the emission also. Structure C is the same, but the UV surface lattice resonance is tuned at the excitation because we are going to excite our photoluminescence with a helium-cadmium laser at 325 nanometer. And structure D is just simple rod, so of course you don't have any anisotropy, just a reference sample. So the second part is to look at the photoluminescence of those nanostructures. So here, this is a photoluminescence maps centered at the emission of the zinc oxide. So roughly it's centered at 390 nanometer. And on the maps, you can see so luminescence coming from everywhere. And the square which are more illuminated are the nanostructures of aluminum, where you can see at the first glance that there is a clear enhancement due to the coupling of the underlying layer of zinc oxide with the structures. If you look at the different structures and if they are sustaining surface lattice resonance or just simple localized surface plasmonic resonance, you can first see also that SLR appears to be a much better enhancers for the zinc oxide luminescence. So we are going to speak a little bit about that after. So the maximum enhancement appears to be for structure C. And structure C, if you remember, this is the one which is tuned at the emission, at the excitation of the laser. Okay, so if you look just at the 2D photoluminescence intensity in function of the wavelength, so this is the upper spectra, you can see that the reference, you can have, if you compare to reference, an enhancement of photoluminescence up to 3.5 factor. You can also see some slight change of wavelength for structure B that we are going also to discuss a little bit now. So let's emphasize, sorry, on the structure C, which is the one which is tuned at the how to say the excitation. So as you know, there is an anisotropy due to the excitation along the short or long axis of the aluminum nanorod. So the idea is to look if we turn the polarization of the excitation laser, if the photoluminescence enhancement it change or not. So this is what we did here. On the first row, you can see a polarization of the laser beam along the short axis of the nanorods. So you can see a clear enhancement, which is circled in white in the maps to the left. And if you illuminate the laser beam polarized along the long axis of the nanorods, you can see that a clear extension, the photoluminescence enhancement. So that means that the excitation enhancement is due to the local field pumping of the nanorods. And if you do not excite the good plasmonic resonances, you will not have a better enhancement compared to the case if you illuminate on the good axis. To confirm the results, of course, we checked on the nano cylinders, which are not polarized, and we find out that there is no enhancement depending on the polarization states. So this is a good way to clarify that at the excitation, when you use the excitation mechanism, which is the one here, so the one to the left, I don't know if you can see my cursor or mouse. If you use the absorption enhancement, it will clearly depend on the polarization states of the impinging laser beam. Now, if you look at structures B, which is tuned at the emission, not at the excitation of zinc oxide, there is some different mechanism. And what we did, what we remark, is that there is what we call the luminescence. I'm sorry, I cannot see my slides. Spectral shaping. So what does it mean? That means that at the emission, the surface lattice resonance, which is the SLR, is going to give a new decay rate for the photoluminescence of zinc oxide. And that's why we experience this shift in wavelength. So at the beginning, we were not completely sure of this mechanism, but we check with a lot of measurements, and we try to reduce the uncertainties on those measurements. And it appeared clearly that for structure B, which is tuned at the emission wavelength of zinc oxide, you have a clear shift of a couple of nanometers compared to the zinc oxide layer, the underlying zinc oxide layer, and for all the other structures. So the hypothesis is that the excitance or the photoluminescence decay relatively into the SLR modes due to their photonic nature, which is explained why there is such a shift in the luminescence. Yes, another stuff, but I did not mention that here, is that if you compare the luminescence enhancements in blue due to the classical LSPR compared to the surface lattice resonances of the hybridized mode, you can clearly see that there are better enhancements for photoluminescence. So that means that the hybridized plasmonic structures, which are very better actually to enhance the photoluminescence compared to classical plasmonic resonances, which are not coupled to the Rayleigh anomaly. Yes, we also look in the visible band of zinc oxide, and here the results are less far, I would say, exciting, but still there is some stuff. Okay, 3 minutes. I'm almost done. So in the visible, so the mechanism, the expected mechanism are not exactly the same, but here you can see, oh, my screen is going on by itself. Okay, so in the visible here, you can see that depending on the polarization, you have not a very clear effects that we can see, because here you have photoluminescence mapping in the visible. So there are, it's a mapping of the luminescence centered at 3 nanometer of wavelength. But still, we can see a slight enhancement of the visible luminescence, but it's located for structure C also, meaning that only the photoluminescence enhancement is only due to the more concentrated field at the excitation. So this is just excitation enhancement actually above the band gap, which give subsequently better enhancement of the visible defects. So less exciting results, but still some effects on the band edge, on the visible luminescence of the oxide. Yes, so I'm going to conclude. So what we did in this study, so we successfully fabricated hybrid structures with sputtered zinc oxide film and aluminum nanostructure on top, which was quite challenging for our engineer. So the surface lattice resonances, which are hybridized modes of plasmonics arrays with Rayleigh anomaly, appears to be better photoluminescence enhancers for zinc oxide films. So roughly it's a factor 3 compared to a factor 2 with classical localized plasmonic resonances. We succeed to unveil different mechanisms of the Purcell effect when you tune your structures to the emission of zinc oxide, an enhanced excitation when you tune at the pumping wavelengths, and we also show that there is a clear polarization dependency. of the zinc oxide luminescence as excitation, which is very promising for future optoelectronics nano devices application. You can find more information in the paper, which is recently publicated. So what we want to do now is to try to have a better control on the photoluminescence of zinc oxide, both in the UV and visible. So we are going to work on double Fano or double hybridized mode with one Rayleigh anomaly in the visible and another one in the UV. We also going to try some new design sample. What happens if we take a single zinc oxide crystal and in the vicinity of an aluminum array? So it's much more challenging in terms of fabrication, but I think it will be very interesting in terms of interaction mechanism studies. And we also try to start some power enhancements, power measurements that you can see on this figure, where you can see in the black curve actually, which is the reference zinc oxide film, and the colored curve are coupled zinc oxide with aluminum particles. So you can see that the slopes is different due to an increase of the pumping rates. So unveiling that there is a better pumping rate in the vicinity of the nanoparticle. So maybe we are going to deal with more power also. Thank you very much for your attention. If you have any question, I will be pleased to answer.
Thank you very much for exciting talk. Are there any questions from audience? Let me check in the chat. So I don't know in the chat, are there questions from here? Maybe you can comment about the oxidation of aluminium. How does that influence your measurements and this enhancement?
Actually, yeah, I see. Can you still see my presentation? I'm not sure.
No, not anymore.
You stopped sharing.
Yeah.
Oh, yeah. Sorry.
Now we can.
Now we can see, yes.
Okay, so aluminum, yes, it's a good question. Actually, aluminum oxidized, that's true, but we noticed that it's very stable in time. Actually, we did some paper about that. If you use aluminum for plasmonic resonances, you will have a slight redshift the first 2 days, but after it self-passivates, and the resonances are very stable in time, at least for 6 months, I would say.
Okay, that's interesting. Thank you very much for the answer. Okay, if there are no any more questions, then thanks again.
Thank you very much.
I will invite the next speaker, who will be Jose Abad. He's here physically. Please.
No se sabe, ¿no?
No, vale, no.
Vale, pues a ver si...
Escritorio, ¿no?
Uy, estaba abierto aquí.
Ahí.
Es para ver el otro mismo. Se había quedado abierto. Ahí está.
Y en el Zoom ya está.
Abres y ahora vas a Zoom y compartes aquí. Puedes compartir solo la presentación.
Mejor. Vale, y aquí era el láser, pues ya no se veía.
Ay, ahora no nos deja porque...
Vale, bueno.
Sí, mira, está aquí. Vale, ya está.
Okay, good morning. Thanks, Mr. Chairman, for the introduction. And first of all, I want to give thanks to Javier and the organization to let me the opportunity to show today my work. I am Jose Abad from here, for the Technical University of Cartagena, and today I am going to talk about the Haxpex technique applied to solar organic cells. Well, a short outline about the talk is the following. My research group is devoted to the study of advanced materials for the production and storage of energy. In Spanish, the acronym is MAPAE. Here, I show you the web page of the research groups, and there are many lines, but the three main lines in which I am involved mainly are batteries, organic solar cells, and electrochromic devices. Today, I am going to talk about only organic solar cells. Well, the experiments were carried out at SPLine, that is the Spanish beamline, and the ESRF, the European Solar Radiation Facility at Grenoble in the branch B. And this beamline is devoted to the study and characterization of varied interfaces and bulks, samples that combine X-ray diffraction and hard X-ray photoelectron spectroscopy aspects. But the first question is, why aspects? But here I show you the universal curve of the electron free path versus the electron kinetic energy. In a conventional XPS, the electron free path is about 1 nanometer. If we increase the photon energy, therefore increase the kinetic energy of the electron, we increase this electron free path 1 order or magnitude more or less to 10 nanometers. In this graph, I show you the probability that the emitted electron reaches the surface versus the electron free path lambda. And for 3 times lambda, the 95% of the electrons reach the surface. So with conventional XPAs, the information depth is more or less 3 to 4 nanometers. And with the Hubspec technique, the information depth increased to 30 to 40 nanometers. Disadvantage, possibility to study varied nanometric layers and also complete devices. Besides, there is a minor contribution of the surface contaminations, and we have access to deeper core levels, as I will show you in the last part of my talk. Well, let me do some publicity about a new XPS-UPS surface analysis system that the next week will be installed in the basement of this building with very interesting capabilities. An electron analyzer 2-dimensional and 2 monochromated X-ray sources of silver and aluminum, and 2 non-monochromated X-ray sources of silicon and zirconium, and as usual, techniques for surface sign as ultraviolet source, photon, ion source, lead. And another interesting capability is that we can cool down the samples until 10 Kelvin. Okay, with this system, we want to fill the gap between conventional standard photoemission and Hubspec technique with the access to these energies. So, okay, let's go to talk about the organic solar cells. An organic solar cell is a sandwich device with different layers. A front and back contact, a photoactive layer, a hole transport layer, or an electron transport layer. The difference between normal architecture or inverted architecture is only the sense of the electrons. Well, I don't go into detail about the fabrication of these devices, only to say that these different layers need to be annealing at different temperatures. And one of the aims of this work is to understand how this thermal annealing affects the quality of and the properties of the layers, and also the final performance of the device. Well, let's go into a little bit detail the photoactive layer. The photoactive layer is a blend of one P-type polymer, P3HT, and N-type molecule is PCBM, is a fullerene derivative, and these two materials forms two percolation networks in a so-called bulk heterojunction. Let me show this nice image, topography and contact potential images of the P3HT PCBM blend by means of the Kelvin probe microscopy technique. This technique is also one of the capabilities of our research group, and let me show how it's resolved with surprising resolution the two percolation networks in the contact potential image. Well, let's go to the first example. The first example is an unfinished device with the without the aluminum contact electrode. We use the sulfur of the P3HT as a fingerprint. Why we want to study the difference between P3HT and PCBM in the thermal annealing? Because in the literature, there are some controversy about the diffusion of these both materials in the annealing processes. Well, we use the sulfur as fingerprint of P3HT, and in this example, when we anneal on Earth this sample, we observe that without annealing, there are more sulfur in the surface. This is observed also in the sulfur 1s spectrum, that the lower intensity with the air anneal. The reflectometry neutron measurement that we have performed are in agreement with the Hackspec's results. Measurements were performed at ILL in Grenoble, and also this is PCBN, and also before the annealing there are more sulfur, more P3HT and sulfur, and with the annealing the amount of P3HT decrease with the annealing. Well, let's move to a real device, a standard organic solar cells. Here we can see a typical IV cure, and if we measure this device by Hackspec's technique, again obtain the same results for the unfinished device. There are more sulfur before the annealing, also indicated by the sulfur 1s spectrum. Well, now let's consider a very simple model to study the annealing in vacuum of a standard organic solar cells. In this very simple model, sulfur signal is the substrate signal, and aluminum signal is the overlayer signal. It's an interdiffusion linear profile model. It's really very simple, but it works with two parameters: the overlayer width and the diffusion width. With these equations, and here I show you the experimental results of the sulfur intensity as function of the kinetic energy of the electrons. And the lines are the fittings of the model, and the agreement is quite good. The model gives us an overlayer aluminum width of 38 nanometers and a diffusion width of the sulfur that decrease with the annealing temperature. Here we can see the very simple model, but indicate that in the surface there are more sulfur, more P3HG before the annealing, in agreement with the previous results. Well, one capability of the Hartz-Stress technique is that we can take high resolution spectra. Here I show you only an example of the aluminum with the metallic and oxygen aluminum to observe the evolution with the annealing. This is only an example of the capabilities of this technique. And let's go to an inverted organic solar cells. Now, the back contact electrode is not aluminum, and it's okay. For this kind of device, we observe that the amount of aluminum is higher without annealing than after the annealing. However, here at low photon energies, we are more sensitive. There are similar sulfur content for the annealing panel. If we move to vacuum annealing, here at low photon energy, we observe that there are more sulfur after the annealing, by contrast with the previous result obtaining for the other devices. Well, one advantages of the experimental setup in Grenoble, in Spanish beamline, is that we can perform simultaneously aspects, spectroscopy, and X-ray diffraction on the same sample. So we can follow simultaneously the compositional and the structural changes to obtain a complete information. Well, so let me show the last part of my talk. There are very recent experiments from last November, and here we study the magnetic photoactive perovskite in a methylammonium lead iodine perovskite. We replace some lead ions by manganese ions, so give some magnetic character to this kind of perovskite. And we're interested to know the manganese oxidation state. If we see the lead for F and the oxygen 1s spectra, there are not so much difference in the lead. There's a little seed inside of the experimental error, and in the oxygen, we can maybe decompose into components. But we're interested in the manganese oxidation state. If we go to the region of the manganese main peaks, we observe that there is an overlap of many peaks. The manganese 2P and the lead 4P are completely overlapped. Here we can see the iodine core levels, and even the indium core level is also observed for the subset. So with this kind of spectrum, it's really very difficult to resolve the oxidation state of manganese in the MAMPI samples. Okay, we take advantage of the Hartz-Stress technique, and we can go to deeper core levels. So we go to the manganese 1s core level. There is no overlap with any other peaks. We go to more or less higher than 6,500 binding energy electron volts. But the problem is that there is not too much information in the literature, and need of standards are required. Now we are carrying new experiments, and in a couple of months we come back to Grenoble to finish we hope to finish these experiments with more standard to clarify the manganese oxidation state. Some changes are observed, but we need more standard measurements. So to conclude my talk, different kinds of organosolar cells and thermal behavior and their backing on air conditions have been studied by Hex and X-ray diffraction. For the photoactive layer alone, and the standard organosolar cell, is found that the thermal annealing under air conditions induce the diffusion of P3ST to the surface. Also, for the thermal annealing under vacuum condition, we obtain the same results. And for the inverted organic solar cells, the thermal annealing under air condition induce the diffusion to the P3ST to the pool. But when the annealing is in the vacuum, the process is inverted. Well, and also finally, I would like to show you that HackSpecs is a very useful technique to study samples where the core level overlap is a problem. Finally, I will give thanks to my colleagues of Advanced Materials for Production and Storage Energy Group of the University Polytechnic of Cartagena, Padilla, Antonio Fernández, Chencho Santos, Antonio Urbina, Carlos Toledo, Rodo López, Juan Fran González, Sebastián Lorca, and of course, the people of Spanish Beamline, Grenoble, Germán Castro, Juan Rubio, and thanks for the money, for the support of the national government and also for the regional government. And of course, thank you very much for your kind attention.
Thank you very much for the interesting talk. Are there any questions? If there are questions from the audience online, please do not hesitate. Just switch on your mic and go ahead.
So I would like to ask something you were showing this spectra before, where there was a huge difference between I think it was the manganese and the lead profile, and the lead you could see two peaks. What is one exactly looking at in this? Or even in the previous slide it was clearer here, for instance. So
okay. The information that we have of the, for example, for the lead for Fs is there you can observe a very small shift. This shift is related with the chemical state, but in this case the shift is 0.2 EP, and it's really in the experimental error of the measurement. In the other spectrum, we can see two peaks at different energy. So we can deconvolute in two peaks, but this is preliminary results. We have to take care and be very carefully to play with the complete puzzle to try to understand this. So we need more information, and the information will be obtained with the manganese, because and the other, to lower energy, to lower binding energies, is really quite complicated to try to extract information here in this. This is complicated.
Thanks. Are there any other questions? If no, then thanks, speaker again. The next speaker, Soqueras. So if you are there, please, you can start share your screen.
Okay. Can you hear me?
Yes, we hear you very well. And now we see also your screen. So it works fine.
Okay, it is in full screen.
Yes.
Okay.
So you can start your.
Okay, thank you, Mr. Chairman. Good morning to everyone. First of all, let me thank the organizers for the organization of this workshop and for giving us the opportunity to present our work. So the title of my talk is Functionalizing Hydrogenated Amorphous Carbon Thin Films with Vapor-Grown Metallic Nanoparticles. So a brief outline of my talk. I will start with a very short introduction about amorphous carbon materials and information about some nanocomposite thin films. Then I will proceed to describe the deposition methods, the unusual deposition methods used for the deposition of these kind of materials. And then on the last part, I will discuss some optical properties and tribological performance of these hydrogenated amorphous carbon nanocomposites. So amorphous carbon is an amorphous network of carbon-carbon bonds or carbon-hydrogen bonds in the hydrogenated form. Each carbon-carbon bond can be either sp3 or sp2, and the content of this amorphous network in these bonds, and also the presence of hydrogen, defines the actual properties of the materials. Considering the terminology, any material above 50% of sp3 content is usually called diamond-like carbon, and hydrogenated diamond-like carbon if there is any hydrogen. If we exclude all the other carbon allotropes, the nanocrystalline diamonds, graphene, carbon nanotubes, these amorphous carbons, they are very versatile class of materials, and they have a lot of applications, passive components in electronics, active layers for sensor, and protective coatings. However, they suffer from high residual stresses in the gigapascal range, which induce delamination, but we're going to discuss about this a little further into the talk. So amorphous carbons, they can be used standalone in a variety of applications. And because they have an excellent chemical inertness, they can be alloyed or doped with other elements, metallic or not, to further increase their potential applications. So since they can be a very good host material for nanocomposites, in this talk, I'm going to describe you hydrogenated diamond-like carbon nanocomposites with embedded nanoparticles of silver, copper, and titanium. And I'm going to talk, as I've already said, about their optical response and tribological properties. All these films have been deposited here at the Research Unit for Nanostructured Material Systems at Cyprus University of Technology, using our hybrid deposition system. And we call it hybrid because it has two main material sources, one PVD and one CVD. The CVD-like source, it's actually an ion beam source based on an inductively coupled plasma, where we have gases introduced into a chamber, the discharge chamber, and they get ionized by the RF power. And using a two-grid extraction system, by applying a voltage, we can extract ions from the plasma, forming a beam, a direct beam, towards the substrate. This beam can be used for deposition, cleaning, etching, or patterning of the substrate. And in our case, by using methane, hydrogen, and argon mixes, we have deposited the amorphous carbon thin films. The second source, the PVD source, it is called also a cluster beam source or nanoparticle source. It's a modified magnetron sputtering, which produces nanoparticles directly at the gas phase. So this source has this magnetron head where the sputtering occurs, and the sputtered atoms, as they travel through a high pressure zone, they nucleate and growth at this area. As they exit through an orifice, they are inserted into a quadruple mass spectrometer, where, because they have negative charge, by using the spectrometer, we can evaluate, we can see the distribution of the diameters. Also, we can fix the values of the spectrometer and narrow down and select only to pass only one diameter. We can control also at the beginning the nanoparticles by changing the parameters here in the aggregation zone, which are dependent on the material being used. So for the filter, we conducted some studies with TEM and AFM to evaluate the capacity of the filters, and we have seen a very good match between the nominal selected diameter of the filter and the experimental value. And when we operate the system in the soft landing regime, where nanoparticles land on the deposition surface at very low kinetic energies, at thermal energies, the nanoparticles are round and monocrystalline in nature. So some information about the matrix only the pure hydrogenated diamond-like carbon films, as deposited with the ion beam source. We have a good control of the kinetic energy and the deposition rate using that source. We can obtain films from 1 to 150 nanometers in thickness, and with densities change from 1.6 to 2.1, with very low surface roughness values below 1 nanometer. And in general, we have around 50% of sp3 bonding with a hydrogen content around 20 to 25%. The optical values of the pure films have been extracted by fitting UV reflectivity curves, and we have seen that we have transparent thin films with low extinction coefficient values and with refractive index span from 1.7 to 2.4. Now let's consider only the nanoparticles produced by the second source. We can control and deposit the nanoparticles on actually any substrate given, from polymer, metal, etc. And we can range the coverage from sub-monolayer to full coverage, and even continue further to form porous thin films made of nanoparticles. As I have already told, we can also change to have a narrow or broad distribution of various sizes of nanoparticles with variable kinetic energy, with good crystallinity, and we can see the plasmonic properties of these. And actually, until now, we have successfully deposited nanoparticles with all these elemental metallic elements, and we're in the progress of producing compound nanoparticles based on transition metal nitrides. Before seeing the properties of the nanocomposite thin films, let's see what happens when we introduce metals to the amorphous carbon matrix. We have seen experimentally and by simulations that metals actually do affect the amorphous carbon network. And what they are doing is exactly at the interface, when these two species are in contact, metals graphitize, change from sp3, the carbons hybridized in sp3 to sp2 form, and we see the formation of graphitic rings. These graphitic rings surround the nanoparticle in this case, or this can be done also with single atoms, which also graphitizes the area around it. This effect, this matrix graphitization, could be useful or not. It could be useful for some mechanical properties, or not useful for the optical properties of the film. A common approach usually to fabricate this kind of nanocomposite thin films based on carbon and metals for many groups is to deposit both species, carbon and metal, and nucleate the metal, taking advantage of the bad wetting of these two species, to nucleate and grow these nanoparticles exactly on the deposition surface around carbon. This results in an extended interactions between the metal and the carbon and a significant reduction of the sp3 content. Even reducing the amount of metal that you introduce into the nanocomposite during deposition, this can lead to atomic dispersion of particles of metals, which can result to even more reduction of the sp3 and more enhanced graphitization. So for us, by having this independent control of the matrix and the already formed nanoparticles, we skip this growth and nucleation on the deposition surface, and we can contain and reduce these interactions. But beyond that, we can use this type of sources to obtain a variety of nanocomposite thin films from small to high filling factor with monodisperse and polydisperse nanoparticles. And also we can control with the same running the termination or the actual surface of our samples to be a very smooth surface terminated with carbon, or we can leave, since we have a good control on the deposition rate, we can leave nanoparticles close to the surface or half exposed, maybe in order to interface the sample with the environment. So for the optical properties, we have co-deposited hydrogenated diamond-like carbon plus metal nanoparticles, silver and copper. By doing that, we have seen that we have obtained homogeneous thin films in terms of density gradient along the thickness without layering and with very low values of roughness. As we can see here in the optical properties, the transparency is retained, especially for the nanoparticles with copper, and the small amount of silver that is inside the nanocomposite, the nanoparticles, has led to the manifestation of the LSPR of silver. And because of the transparency, we believe that also the copper LSPR has even showed up in the spectra of the extinction coefficient. The refractive index spans a little further from 1.5 maybe to 2.5 for these films. And this is telling us that we have successfully kept the matrix of the system of our samples transparent, while in a previous work we have exploited the matrix graphitization by introducing silver again on into amorphous carbon matrix, producing films with high absorption and a broad absorption to match the solar spectra. So this is leading us, this control, the independent control, to think about potential application, for example, for specific targeted reflective coatings, maybe with antimicrobial properties for various biological applications, or to use all the benefits of protective coatings of the carbon with some embedded photocatalytic and photoactive nanoparticles, and all depend on the type of and chemistry or the elements that you introduce into the carbon matrix, which also can be even further tuned by changing the plasma parameters and add some doping elements like, for example, let's say nitrogen. So there's a lot of potential on that. Going further to the mechanical properties, as we have said, we know that these types of hydrogenated or in general amorphous carbon films suffer from residual stresses. We sequentially deposited this time hydrogenated diamond-like carbons and nanoparticles. This time is silver and titanium. We've seen that even a very small introduction, minor amount of these nanoparticles significantly reduces the residual stresses of the films. Apart from these low filling factors can have these benefits to our system, also the introduction of complete nanoparticles does not allow these nanoparticles to diffuse into the system as we have seen atoms do when they are atomically dispersed into the system. So in order to perform the tribological evaluation of these films, we performed the nanoscratch test, which actually is a fixed hard intender with a load, and the material is sliding against it. By doing this nanoscratch test, we have seen 4 different critical loads, one load for the transition between the elastic and the plastic region. The next 2 critical load 1 and critical load 2 are correlated with the formation of cracks and the propagation of cracks into the material. And then the critical load 3, which is the complete delamination of the coating. All these regions can be easily depicted here on the SEM imaging, and especially the last part, the delamination. By evaluating these 3 different, by seeing these 3 different SEM images of pure amorphous carbon with silver and titanium, we see how this introduction of metallic nanoparticles, both silver and titanium, have improved our material, have increased its ductility and toughness, and have increased its abrasion resistance. All the critical loads 1, 2, and 3 regarding the crack and delamination, the values were higher for the nanocomposite compared to the pure hydrogenated diamond-like carbon. And finally, I'm finishing. I'm almost at the end. We have evaluated the friction coefficient of these coatings, and we have obtained very low values of that, measured it and evaluated at the elastic contact regime. All the low values of the friction coefficient are attributed to the formation of tribolayer, which acts as a solid lubricant between the probe and the film. And we have the lowest value when we introduced silver nanoparticles. We think that because of the plastic, of the softer nature of the silver nanoparticles. So some conclusions, very in short, we have successfully synthesized this kind of pure and nanocomposite thin films using our hybrid deposition techniques. We have very good independent control of the matrix and the nanoparticles, which increases our versatility to the available and accessible to us nanocomposite layouts for a plethora of applications and material combinations as well. And at the last part, I have presented you the optical properties, the less PR manifestation, the friction values, and the reduction of the residual stresses of the film. So let me thank you again, the organizers, for the organizing this workshop, our funding institutes, and also you for your attendance. Thank you very much.
Okay, thank you. Lots of applications for these materials. I think we have time for one quick question, if there are any. If not, then thanks, speaker, again.
Thank you very much.
And I will invite the next speaker, who is Oswald Sverners. I hope, yeah, I see Oswald is here. So please go ahead. You can share your screen and start your talk, please.
Thank you for the kind introduction. And if I may, I would like to start now.
Yes,
okay.
please. The presentation is visible, so thanks.
Yeah. So hello, everyone. And this is my pleasure to introduce a small computational study of composite materials based on a polymer matrix and crystalline Gotthard nanorod inclusions, and for the application of type of electric devices or energy sources, for that matter. The study has been partly experimental and simulation based, and for that reason, I would like to thank also my colleagues and mention all the colleagues who are involved in the experimental part, whereas my own results will be mostly focused on the simulation results. To give a brief introduction of this agenda of type of electric devices and applications, as you may remember from yesterday's presentation given by Arne Schutke as well. I'd like to briefly introduce the main concepts, and those would be firstly the employment of the contact electrification processes due to mechanical interaction at the solid surface contact due to mechanical external forces. And the second principle, which is made use of in these devices, is based on the concept of electrostatic induction after reversal of the mechanical loading. And thereby, by adding or connecting to an external electrical load path, we may harvest the electrical energy and accumulate or just drive a device as a standalone. And as the image suggests, then there are diverse possibilities of setting up such devices in terms of movement types and architectures as well. What motivated this particular study is based on the idea that by adding a certain nanoparticle-based additive to a polymer, we may, under certain conditions, observe significant improvement of contact electrified charges, as the preliminary tests would suggest, against different contacting surfaces as well. And what motivated us for further insights and investigation was the potential identification of the optimum content of these particles, so that we would get the most out of this approach. And as it was mentioned, the initial material used for the matrix part of the composite was PBA polymer. As these plots indicate, then we could initially observe a correlation between the physical properties, in particular properties related to gas transition, and the accumulated contact charge after contact electrification. And what remained as a first question for further understanding of this problem was the driving forces behind these behind this behavior and dependence on the particle content. And what helped for this purpose was firstly the hardness distribution of the contact surface on the different concentrations of the particles. And what was interesting to see was that there was indeed a very similar change in the maximum hardness and also the inhomogeneity of the surface properties, depending on the particle content, in a very close similarity with the phase properties on the previous slide. And what motivated our further interest was more chemistry-based or physical chemistry-based explanation and interpretation of the behavior and dependence on this concentration. One way to explore this was by means of, on a micro scale, let's say, was simulation by means of finite element method. And by this, we could estimate somewhat similar distribution of stresses on the surface under a compression contact condition, considering pure polymer and the polymer with a 10% increased stiffness inclusion in the middle of a cylindrical, half cylindrical geometry. And what we could see was somewhat similar to the mechanical hardness distribution. And what was important to notice in these results was also the dependence on the direction of the loading in terms of stress components. And at least at this point, more like theoretic, but still plausible prediction as to what would happen if we increase this kind of inclusions up to a certain level, so that these regions of gradient would start overlapping. So that also indicates that there could be a second reason for the reduction of the contact electrification performance at higher concentrations, given that at this level the stress gradients might actually be reduced again for that reason. And additional interest was identifying, at least on a theoretical level, possible alternative for the matrix material, which was initially the already mentioned polyether block amide polymer. And for that purpose, we considered different selection criteria, either based on just different kinds of non-bonding interactions at the matrix inclusion interface, as compared to elastomeric properties, which are known to be significant for polymeric-based dielectric materials, and also very well-known materials with favorable charge transfer properties due to the affinities of electrons, like polytetrafluoroethylene in the considered study. And for this purpose, the two methods that were employed were the classical force field type method without polarization, known as universal force field potential, and somewhat more recent, partially polarizable force field named GFN-FF. And given the scaling of these methods and computational limitations, they were considered both non-periodic and periodic structures. So in this figure, you may see the non-periodic case studies for small polymer fragments placed on a contact surface. And for these structures, we compared the total absorption energies, both under thermal and static energy conditions, in terms of the total potential energy and the components of the energy as dispersion and the hydrogen bond based energy components. And from these we can learn that firstly, there was a significant effect of the thermal effects, in terms of these change of the absorption energy, meaning that the static differences between interactions in the matrix and at the interface were much more significant as compared to the room temperature and dynamics. And in terms of the energy components, we could immediately observe that the change of the respective energies was more pronounced for the hydrogen bonds in case of PDMS and PTFE polymers, whereas for the PBA polymer, this was the other way around, meaning that the dispersion energy was played a more significant role in a potential strengthening of the interface between inclusion and the matrix. And these will be the same already mentioned conclusions in a brief form. And to mention further, and as a second part of the computational study, I should introduce the results of periodic system-based simulations, which include the same polymers, but using this non-polarizable force field. And for that reason, I should mention first that indeed there were certain differences in the absorption energies under identical conditions to be observed. And for that reason, we had to be rather careful in drawing the conclusions for the applicability of these polymers with respect to each other. And what we could see, however, in agreement with the previous polarizable force field result, was that indeed there was rather significant increase in the density for the PDMS and PBA polymers as compared to PTFE, which was indicating actually only partial increase in the density on one side of at one interface, whereas at the other, the bulk density, which is identified with this dashed line, was approached very closely. So that was in fair agreement with the previous result of pure absorption energy based results. And with that we could estimate at least roughly the distribution of density as it may, and thereby we could draw these parallels with the experimental results in terms of changing harnesses. And of course we had to take into account factors like time scale of the simulations and size effects, which definitely would had to be taken into account to draw final larger scale conclusions regarding comparability of these materials. And with that, I would like to round up with a few main conclusions from the study. Namely, firstly, we could draw distinct parallels between the mechanical stress distributions and the phasement content, depending on different concentrations of the particles in the composites. Second, we could, at this point at least, based on purely theoretical calculations, we could identify PGMS as the most promising matrix candidate for further studies due to the strengths of the interactions at the interface. And further conclusion could be drawn that there may be a weak correlation with the elastic, and for that reason, the phase properties of the considered polymers, given the similarity with the absorption energies. And last point, which is equally important, is that experimental validation of the comparison between these mentioned polymers is pending, since there may be many practical or physical factors due to production of these composites that may have not been taken properly into account at this point. And with that, I'd like to express thanks to the supporting agency which funded this research. And thank you for your kind attention.
Thank you. Thank you for the interesting talk on these computational studies. So, are there any questions from audience? If there are no questions, then I would like to thanks again, speaker. And I would like to invite the next speaker, Kathleen Poppa. Please, if you are there, please, you can start to share your screen.
Hello.
Hello.
My name is Alexandra Ciopoi, and I will be speaking and presenting on behalf of Mr. Poppa Cătălin.
Okay, very nice. Okay, please. So if you are ready, you can share your screen and start your speech.
I think now you can see my screen.
Yes, we see
Okay.
it perfectly. We hear you. So you can start, please.
Hello, everybody. My name is Alexandra Ciopoi, and I would like to present today our research entitled Controlling Biofilm Growth Through the Electrophoresis in Flow-Based Bioreactors. Bioreactors are considered apparatuses for growing organisms such as yeast, bacteria, or animal cells under controlled conditions. They provide a controlled environment by ensuring the same temperature, pH, and oxygen levels throughout the whole system, as well as homogeneous environment by constantly stirring the contents. For this particular research, we have chosen a specific design for this microsystem, which allowed the accommodation of two inlets and two outlets, one for nutrient broth and the other one for bacterial suspensions, as well as a central channel with a width small enough to allow the formation of the formation of a laminar flow. This device itself allows the accommodation of electrodes, one longitudinal or parallel to the central channel, and the other ones perpendicular to the central channel, in order to form a non-uniform electric field and hence the electrophoretic effect. The electrophoresis is a phenomenon by which a non-uniform electric field induces a net force on a polarizable particle or molecule. This non-uniform electric field causes an imbalance in the Lorentz forces produced at the particle poles, both neutral or induced, so that the resultant net force is non-zero and therefore causes a particle motion. Depending on the relative difference between the complex dielectric properties of the media and of the suspended particle, this net forces causes the particle to be either attracted or repulsed by the regions of a high field intensity. To determine whether this electrophoretic effect works in our systems, we have chosen to use bacteria, especially Staphylococcus, which are invasive gram-positive pathogens belonging to a group known as pyogenic cocci. Coagulase-positive species, such as Staphylococcus aureus, are opportunistic pathogens which are known to cause wound infections, abscesses, urinary tract infections, pneumonia, boils, and pimples. Staphylococcus aureus, the one strain we chose was an ATCC strain, which is a controlled standard strain used in laboratory testings. The experimental part, as you can see in this image, the microfluidic systems were connected to tubes, both on the inlet and on the outlet. As on the outlet, we collected the samples separately. These tubes on the inlet were connected to syringes filled with suspension of bacteria and nutrient broth in order to provide sufficient nutrients for the biofilm to grow. As 3 different experiments were carried out, one in standard conditions where the nutrient broth was placed on the right side and the bacterial suspension was placed on the left side of the microfluidic channel. When we refer to the right and left side, we mean right side, the one where the parallel electrode is introduced, so here, and the left side is where the perpendicular electrodes rest. There was another experiment done with switch positions. So the nutrient broth goes on the right side and the bacterial suspension goes on the on the right side, and a zero condition, so a control condition where there's no dielectrophoretic effect induced on the particles in order to control whether the dielectrophoresis works or not. The electrodes were introduced on both sides of the microfluidic channel and connected to an electrical source. In order to characterize the biofilm formed inside the microfluidic channel, we have chosen several techniques, one of which was the optical coherence tomography. As you can see here, we have cut up the system into in order to be able to see both sides of the central channel, both the right and the left side. Here on this slide, we have presented the left side of the channel, of the standard conditions central channel. These images have been taken on different heights compared to the inlet of the channel in order to see the evolution of the thickness of the bacterial film formed in the microfluidic system. As you can observe, we can see the formation of biofilm. However, we do not have a clear image of whether this biofilm is thick or not. We have taken images on the right side as well. Here we can also see the biofilm, the formation of the biofilm. However, we cannot see compared to the left side whether it's thicker or not. To determine this, we have chosen to use an inverted microscope using a multiple image alignment processing function to see a vaster image of the inside of the central channel. As it can be observed in the top image, which presents the left side of the channel, the biofilm is quite thick. We cannot see the bottom of the channel, whereas in the image on the bottom, which represents the right side of the channel, the deposition filaments are quite visible, indicating a thin layer of biofilm. In order to get a better view of the surface of the biofilm that has formed inside the microfluidic devices, we have chosen to use SEM imaging to get a better knowledge of the steps in which the biofilm is visible at that point, because there are several steps which the biofilm goes through in its formation. In these images, we can see the standard central channel, left side of the central channel, which presents a quite thick biofilm, as well as specific structures for the extracellular matrix of the Staphylococcus aureus biofilm. Comparing this to the right side of the channel, we can see the specific deposition filament lines from the 3D printing process, which indicates a shear biofilm formed on top of it. However, the standard extracellular matrix shapes and surfaces can be seen as well. For the experiment where the inlet positions have been switched, so the bacterial suspension went on the left side and the nutrient broth on the right side, and the nutrient broth went on the left side. The similar thing could be observed, that on the left side of the central channel, the biofilm formed was quite thick, with very few regions where identifiable colonies could be observed, as it can be seen in this top image. We compare this to the right side of the central channel, where, as you can observe in the bottom image, the deposition filaments can be are very observable, and therefore we can affirm that the thickness of the biofilm is a lot smaller than the one on the left side of the channel. For the control system, we did not use the electrophoresis, and in this case, we can see that the deposition lines are not visible anywhere, and the thickness of the biofilm is quite great. with identifiable colonies here on the bottom image. In order to have a comparing standard, we have used the same PLA filament to print a plate on which we grew biofilm in standard conditions, similar, but in static analysis, which is a standard form of determining the growth of biofilm. Here we can see the extracellular metrics as well as the colonies themselves very well isolated. Conclusions of our research: these 3D printed microfluidic devices represent an efficient tool to grow bacterial biofilms in dynamic conditions. The OCT imaging showed that the initial microfluidic system, on the initial microfluidic system, there was a biofilm formed on both sides of the system. However, on the left side, where the perpendicular electrodes are placed, the thickness was greater on that side. The images obtained on the inverted microscope show the growth of the biofilm inside the standard channel, suggesting a thick layer on the left side as well. While on the right side, we can only see a very thin layer of biofilm. These observations was also sustained by the SEM images. The 3D printed PLA plate was used to confirm the formation of the biofilm, both in standard and dynamic conditions, as well as to identify the extracellular matrix. And the SEM images corresponding to the left and the right side of the switched samples suggest the formation of a thicker biofilm also on the left side, which suggests in the end that the biofilm formed inside the microfluidic channels was thicker on the side containing the perpendicular electrodes, which represents a negative de-electrophoresis for the bacterial cells. Lastly, I would like to thank you all for this opportunity to present our research. Thank you.
Thank you very much. We have time for questions. Please, are there any questions from audience here? I would like to ask the question. It was interesting to see that you can influence the growth of bacteria, this biofilm, by applying electric field. But is there also, do you have also in mind some kind of approaches to eliminate this growing of biofilm in these microfluidic channels?
Yes, we have done previous research on how we can influence the growth, both by altering the surface of the central channel or by this de-electrophoretic effect on how we can repose bacteria from one side of the channel or both sides of the channel in this case.
Okay, interesting, very interesting. Okay, any other questions? No? So then we can thank the speaker again. This was the last talk in this session, and I think we have deserved the coffee, and see you in the next session. Thank you.
All right. Good morning. Can you hear me?
Yes, I can hear you quite well.
Okay. It's a pleasure for me to chair this session and present the first speaker after the coffee break is Demetri Macias from, sorry for my friend's accent, Université de Technologie de Troyes. And the screen is yours.
Ok, thank you. Bueno, buenos días a todos. Es un placer estar aquí. Y ahora voy a hablar,
Yes.
voy a hablar en inglés.
No.
Podría, pero no. Okay, so I'm going to switch to English. Can you hear can you see my screen?
Yes. Yes.
Okay, okay. So thank you for the invitation to give this talk here and have the chance to share with you some of the results we are doing concerning symbolic regression. Symbolic regression is a somehow forgotten method for artificial intelligence that now has retrieved some popularity, and I will explain you why this could be useful or as a complement for example, deep learning techniques or heuristic optimization techniques. So this work was done in collaboration with Kin-Mong Lee and Alexandre Vial at the UTT. And well, I would like to start setting the context of this work. And basically, over the past decades, there has been a lot of works, experimental and theoretical, dealing with the mechanism of coloration. And basically, those works were focused on biological structure. And one of the most popular is the morpho-retinal butterfly. And well, people were interested on explaining the origin of this blue color. And as you can see here in this zoom, well, it is this color is due because of the geometry. Although there are some pigments, of course, the scale of some material, basically is this Christmas tree-like structure that is also like a grating. So now this has led to some interesting applications in photonics. And not only butterflies, but also you have plenty of works dealing with the structural coloration in jewel beetles, especially those works look at explaining this color, the origin of this color. And here you can see a TEM image of the wing of this beetle that can be, and actually this is the way it's done, can be modeled as a multi-layer structure with B layers that are composed by a high refractive index and low refractive index materials. And well, basically it's a Bragg mirror. So this kind of structures are treated with matrix methods, and that explains the origin of this color. Basically the number of periods, but also the thickness of each one of these layers. And well, we have been working on that because among those works that explain the origin of the color in biological structures, there are some works that have been devoted to describe the optical properties and mainly the dispersion of these structures. And here, well, I have just I'm just writing some references that make use of different techniques to retrieve the dielectric function or the refractive index when dealing with butterflies or beetles. The first one uses effective medium theory. The second one uses an iterative procedure to retrieve from experimental information, from ellipsometric information, the refractive index. And the third preference, it's interesting because it is one of the first that uses a model to represent, to find the dispersion properties of Ewell beetles. They, in this case, they use a Cauchy model to represent the real part and decreasing exponential for the imaginary part. And also, we have been working on that problem too. And in the fifth reference, we try to retrieve the dielectric function of one layer of this beetle's wings using this time Lorentz model. Well, actually, it was a nightmare. I will explain why. So we had to simplify a little bit the problem, and we ended up using Selmayr model, which is not bad for biological structure because the absorption can be neglected in the visible. And in all of these cases, in these two cases, we used what I would call a traditional approach to find the dispersion model, because we established a well-known model, Cauchy, Selmayr, Lorentz, and then we adjusted the parameters that best fit the experimental information. So in that case, there is a previous knowledge of the model we want to use. What we want to do is to go farther than that and use symbolic regression that I will explain a little bit more in detail later, which not only retrieves the parameters of the model, but the model itself. And this makes a big difference with respect to deep learning techniques or neural networks, because neural networks, yes, they establish a relationship between the different variables, but one does not have a closed expression that represents the model. Of course, we are going to use symbolic regression in this case, but I'm sure that it could be used in other contexts, but I will come to that later. So to state the problem, now the context is more or less clear. What we are looking for is to find a closed expression that models the dispersion properties of one layer of this matrix that I have here, that in this case is a simplified representation of what happens with a shell, with nacre specifically. Here you have a mollusk, it's a mussel, and you can see that depending on if the shell has been treated or not, the colors will change. And of course, that is due to the fact that what they call virgin shell here, that is here, it's a column of nacre plates, okay, that have in between an organic layer. This is called virgin shell, and it gives these colors. Then there is a thermic treatment to remove the organic layer, and what they have is, in this case, the nacre columns, but there is no organic layer, so it's as if we had nacre, or in this case is calcite, uh, air, calcite, and so on. So we can simplify the model, we can represent it in this way, and of course we can obtain different spectra that will be associated with different colors. One way to represent or to find the dispersion of this material would be with that traditional technique, imposing some model and go as it is done always. We want to go further than that. We want to use symbolic regression to explore its possibilities and limitations in this case, because that could be quite useful and settle the basis for the design of photonic bio-inspired structures. But the question that one may ask is, what is symbolic regression? Symbolic regression, as I said, is a machine learning technique. And basically, it will try to identify and predict a mathematical relationship between the different data in a data set. And we have two, two possibilities. There are many ways to do symbolic regression, but the ones that are most popular are fast function extraction, that is a deterministic technique that somehow will use a linear combination of functions in order to find the desired, the searched model. And the other one is based on something that is called genetic programming that was proposed, as you can say, in the early 80s. And basically, it will work with three representation of the function. It will take, for example, one branch of these three and will mix it with this other one, and in the end they will have, or they will give, a function. So what we have here, I don't know if it's possible to see it, it's very simple. It's the product of the subtraction of this variable. So in this case we can treat constants but also operators at the same time. And this is what I meant when I said that symbolic regression will give us the parameters and the model itself. There have been some applications in physics. This is not new. One of the seminal papers was the one by Smith and Lipson in 2009, and Nature, and it was used in this case to characterize dynamical systems. Then, for some strange reason, the method, well, was slipping aside, and then in 2016, 2019, well, there was again a gain of popularity, maybe because of the advent of more powerful computers and the advances in programming libraries that one now can find all over the net. And even last year, well, 2 years ago, there was this artificial intelligence Feynman physics inspired method for symbolic regression. So it is not unusual to find this method, but in other contexts different than optics. But well, we said, well, maybe it could be interesting to use it for the applications we are interested on. How symbolic regression works. Here, this is a simple benchmark function that we have here. That will be our target expression. And if we compute this function for different values of x, we have the blue crosses on this figure. We will use this to feed up the white box of symbolic regression that is represented by this flux diagram and all the different stages in this search for the model. And in the end, we will end up with this three representation that if we translate it to equations will give us this expression. In this case, it's quite simple, and you can see that we have retrieved from the blue crosses the same expression we had in the beginning. And if we plot this function, you see the red curve. There is a good agreement between the target expression and the retrieved expression. In some cases, it is required to have a further simplification. To do so, well, we use Python. Actually, all our programs are in Python. We use a Python library that is called Snumpy for symbolic calculus that will help us to simplify the retrieved expression. So basically, and roughly speaking, this is the way how symbolic regression works. I can go into the detail if you want, but not now because lack of time. How can we use that for our case for dispersion functions? Well, we have two ways. We explore two ways in this work. The first is using ellipsometric data because we need a start point. The goal is to find the expression from that ellipsometric data, but also what we have access to is to reflectance information, to intensity. So we also explored the possibility of using symbolic regression using as input reflectance data, and the goal is the same, to have a model of a dispersion. Of course, we wanted to do things gradually, and in the beginning, we started with semi-infinite materials in order to be sure that what we got was right. And well, it is not maybe not very clear here. We have with blue points the target dielectric constant we are looking for, and then with the upside down triangles and the normal triangles, we have the results that we obtained when we start from ellipsometric data, which would be this retrieved expression, and the expression we obtain when we use as input the reflectance spectrum. In order to compare the spectra, here you have the different spectra, and what we can see is that there is a good agreement. However, the retrieved expression, even though they give the same spectra and the same data, do not coincide with this Selmayr model that we have. So in some cases, and most of the times, we don't necessarily get the same target expression, even though we obtain the desired results. So we tested this with silicon dioxide. And also, well, just to be sure that we were not just having chance, we tried with another material, following exactly the same steps. And well, we can see a good agreement between the target and the retrieved data, and of course the retrieved reflectance, even though, once again, the expressions are not exactly the same. And this can be explained because of the random character of the method. Okay, but now let's jump into the water and see what happens when we look for the dispersion model for an acre-like structure. And in this case, we explored the two cases: when the shell has been treated and when it has the organic layer. In blue crosses, you can see the target reflectance spectrum, and you can see here the Selmayr model taken from the literature. And well, these are the results we obtain from symbolic regression when we use this retrieved expression here. Of course, if we related reflectance spectrum, well, we see a good agreement between the target and the retrieved spectrum. If we repeat our numerical simulation, you can see that also we get a good agreement between the target, the expected dispersion model, at least numerically, and we have the respective retrieved expression. So this provides us with some confidence on what we are doing. And we want to go farther than that because, as you can see in these cases, we have dielectric and non-absorbing dielectrics. We want to go farther than that. However, things become a little bit more complicated, and I will explain you why. So, as a summary, well, it seems that symbolic regression can be a suitable tool to retrieve dispersion models. So I'm thinking about this context in particular. We can take into account different geometries, in the case of multi-layer structures, but we could think also about inclusions and that usually are treated with effective medium theory, but I think we could do that with symbolic regression. We could use also multi-objective symbolic regression schemes, which means that we could solve also multi-physics problems. And that could be quite useful if we want to design biomimetic photonic structures. But well, this is something that still is in progress. We are exploring now what happens when we consider absorbing dielectrics. And in this case, things becomes more complicated. Now we know that we can handle complex functions with symbolic regression, but verifying the causality principle is not straightforward. So we are working on that. And one drawback that we know that we experienced from symbolic regression is bloating, which basically can be translated as obtaining awful expressions with 70 terms that, well, you can imagine that are useless. So we are working on that. But well, this is what I wanted to talk about today, and I'm ready for questions if you have. Thank you for your attention.
Thank you very much, Demetrio, for your interesting talk. Now, the session is open to questions.
So I may have one. Is there any intuition that we can use to know when this bloating is going to appear? So when do we have to expect this this growth of the expressions?
I would say always. and I think for what we have seen, bloating is inherent to this technique. One can use some called hyper parameters to adjust the what is called the parsimonial pressure in order to have shorter expressions. But when we do that, what we have seen is that in that case, you are somehow forcing the algorithm to converge to another function that does not necessarily represent what you are looking for. I don't know if I answered.
Imposing too many constraints that bring you to a wrong result.
And yes, and for example, when you have absorbing dielectrics and you have an awful expression with many terms, this does not necessarily mean that it's wrong, that symbolic regression is failing. We tested with Lorentz model, And we ended up realizing that what symbolic regression gives you is the expanded expression of Lorentz model with many oscillators.
Yeah.
So bloating does not necessarily is a problem, but one needs to be careful with numbers.
Well, thank you again, Demetrio.
You're welcome.
And let's move to the following speaker is Thomas Mauger from University Technology Dev, right? Sorry for my friend's accent, and the screen is yours. Okay.
Hello, everybody. Can you hear me and you see my screen? Yes, it's okay.
Yes, we see your presentation.
Okay. My name is Abdelhamid Mima. I'm very happy to present you our work. And I thank you for the organization of this workshop. So today, I would...
One second. Can you put the presentation in the screen, the whole screen? I think that it should be...
It's okay now?
Okay, perfect. Thank you.
Yes, I continue. Today, I would like to talk to you about one area of our team of mechanoplasmonic. This team is managed by Professor Thomas Morer and Associate Professor Julien Proust. And me and some colleague of PhD students also participate to this work. So today the topic is flexible plasmonic, and question what we want to answer is how to integrate strain monitoring into Meta. So first, in industrial application, we are looking to have a safety system, and for this we need to understand how the materials take how the behaviors of stress in the materials. So for this reason, generally industrial replace the metallic pieces after thousands of cycle of utilization, and they complete this safety system by using some sensors, some sensors like resistive strain gauges or Bragg mirrors to have an idea about the stress or the strain. So this kind of sensors give very sensitive information about the stress, but present the disadvantages, the inconvenience for we should have electrical circuits in near the system, and we cannot put it everywhere for some specific emplacement for in the system. For this reason, we looked for a solution for these markets, and we look for how to give large strain monitoring like more than 1% of deformation, and have a system without contacts and without adhesive layer, and be easy to use for the engineer or technician that make the measurements. You can see in the right image and system that can offer some point of what we look to do. They use birefringent resin that change with stress when we apply stress. That we can see the color. That means that stress. It's the intensity of stress. It's not the same. So this application, this technology, to answer to this need to test technology, we need to look for how to integrate optical strain sensor into metal and answer to this market niche. So for this, I will present you the outline of my presentation, and starting by just a quick introduction for in situ ECM nanoparticle displacement. And after I present you how we can do measurements of strain by optics. And after, I will present you some realization made by our team. So, in general, we use periodic grating to measure, to have a mapping of the strain. And this is used to understand how the boundary grains of the metals change when we apply a stress. This is very important in several applications. For example, for oxidation or for high temperature oxidation, we need to understand how the boundaries, how the grain boundaries moves when we apply a stress. So this periodic grating on the deposits on the metals can help us to understand the evolution of the grain boundaries. In the right, we actually use mapping of the surface of 3D printer of metals. It is for additive pressure of materials, and we use it to understand how we can predict the fire of the system, the cracks and their propagation. So now we have an idea to have the mapping, but experimentally how we did it. So I show you just a general evolution presentation of the evolution of stress. This is macroscopic evolution. We can see the steps of the evolution of the strain, and we can see in the image in the down, we put on the surface of the metal a gray of nanoparticles. That dimension of it's around 200 nanometers, and the dimension of this grid is adapted to the dimension of the grain. Generally, the grain it's from 10 to 100 microns surface. Oh. And we take images. We take images from in situ ECM measurement, and after this, we calculate the displacement of each pitch over all the evolution of the stress of deformation. So in this image, we can see the several steps on the evolution. We start by by A, from A to E. And we can see when we started, the deformation is it's very quite zero. And when we start to apply stress, we can see that in the position C, in the curves, we can see that the appearance of a band where we can see that the displacement of this pitch start to be big, and if we continue to if we continue on to applying stress, we can see the evolution of this band and the apparition of other bands in the position of D, and after this we arrive to the final position A and just near the cracks. We can see exactly how is it the shift of the position of this pitch, and after we calculate the strain of the strain of the all strain and tensors we need for calculation. These works help us to give an information of the stress or in general, but we cannot buy it like this because we need to buy also ACM, but it's not our objective. Our objective that, like I said before, we need to have strain mapping, but without contact, and have the same parameter of companies or industrial like. So for this, to ask to test niche, we need to see what happened in strain sensors in optics. So this we think to plasmonic effects that allow us to understand what happened when we apply a strain and we have a nanosphere of gold deposited on the surface of flexible surface, and depending on the polarization, we can see that we have a shift of the resonance due to the stress applied to the substrate. So this depends on polarization. It's normal because if we see here, when we apply in the X direction of the strain, we can see that the particle goes far from each other. And if we can see what happened in the other direction, in the Y direction, when applied strain, the sphere approach and the electric field enhance, and the gap decrease, and this creates a shift of the resonance. So this work gives us an idea how to use this kind of phenomena to shift the resonance. Other studies down in our team using the grout deposition of random nanoroots on the flexible substrates. In this case, it was PDMS. And in the same, we have a dependence on the polarization. And we use this to calculate the shift of the resonance when we apply elongation. So we actually, this study showed that we have 2 nanometers by 1% of change in strain, and give an idea how to use the plasmonic effect to measure the macroscopic elongation. So how we can do tests in flexible substrates? So if you want to have a mapping of the surface, we need to have a regular grating of nanoparticles, and we put it into the flexible substrate. So For this, we developed a process of transfer of nanoparticle to flexible substrates. In our case, it's PDMS. And this work is based on the work of the team of Florian Lay. So in first, we deposit sacrificial layer, it's a metal. And the second time, we do EBL lithography to deposit our grid of nanoparticles in the surface. And after this, we functionalized the surface of this gold nanoparticles. After this, we cool the PDMS on the surface, and the next step, we etch this sacrificial layer by wet etching. In the end, we have all the grid of nanoparticle inside PDMS, and we can after etch the PDMS to have the nanoparticle on top of the surface of the PDMS. I will show you an example of some realization made by a PhD student and colleague William. And we can see in the right that this structure was deposited on the tensile specimen and the top of the surface in the center of the tensile at specimen. And we can see that almost of the particles are transferred to the PDMS surface. So now we have an idea how to integrate grating of nanoparticle to the surface of PDMS and flexible substrate in general. But now we focus to each pitch and try to understand how we can make a big shift of the resonance of the when we apply strain. So we looked for chiral structure, and because this structure is used for chiral sensors, and now we focus to use this kind of structure to our application, that's mean strain sensor. So chiral structure, we presented like the parameter that we need to calculate. It's circular dichroism. It's just a difference between circular polarization left and the right, and we have in the blue in green line, this is the difference between the two polarization. So as you can see in this structure, we have several parameters to adjust to increase these parameter. Okay, when we apply strain, the satellites change, turn and move, and we try to improve this parameter to have the maxima of value of the dichroism. That's mean difference between left and the right circular polarization. So this simulation gives us an idea of change of dichroism just on 20 to around 50, just with 0.12% of deformation. So this work it's the work of Florian Lamaze that make experimental realization of this structure on glass, and did the first experimental results that we can see that the value of the spectrum of the dichroism, it's not approach the FDDT simulation, but this can be explained that in simulation we don't take angle of incidence that can be made in experimental measurements. So actually, we are performing the parameter of this structure to increase the value of the circular dichroism with stress. Other structures are also studied in our teams, that like dimers and chelates and random nanorods, to confirm that first we find the similar results from transfer of nanoparticle to flexible substrates, and after to have another kind of structure that allow to optimize the efficiency of the extinction, and also measure some degenerations of plasmonic modes. This work is part of collaboration with William in our team. So these structures are made in PDMS and transferred by the process that I present in few slides before, and we can see that the structure transferred to the PDMS, to the surface on PDMS, and we have really good quality of transfer. And I just want to say that now we try to optimize this structure to have a large shift of the resonance of our structure. This is just a result of the dimer structures on glass and on PDMS. We can see that it's really similar. We have a shift of around 25 nanometers between 30 nanometer and 100 nanometer of gaps between this, and depend also of the polarization. So in this measurement we don't apply any stress. So I give you an idea of our work in this team. We have some work on mapping of strain using mechanical metals, and now we go to do some mapping for flexible substrates without contact, using just the phenomena of plasmonics effect. So to finish this presentation, I hope that I give you an idea general, and this allow you to create some collaboration and express you some needs. For example, for ECM nanoparticle displacement monitoring for strain mapping on general on flexible substrates. We will be happy if you have any question, and to create some collaboration after. Okay, this is the end. Thank you for your attention.
Thank you, Abdel Hamid. The time schedule is really strictly, and we have enough time for a very quick question.
Yes.
So maybe I missed it, but maybe a quick word on how strong is the strain? I mean, is this something that you can change the color of the object by touching it, or do you have to really apply a large strain?
Sorry, can you repeat the question? I don't understand.
Yeah, you mentioned that the color, let's say, of the object changes under strain?
Yes, we need
When you stretch them?
We need to move the color in the visible, and now exactly.
I think that the question is about the amount of strain, no?
Yes. How many newtons, if you want?
Yes. How we can translate the colors to physical magnitude on the strain, no?
Yeah, correct.
How, if I understand your question, you mean how much shift is it?
Yes.
Actually, we if you can see in this image, typically for dimmer, for example, we can have 50 nanometers of the shifts around from 10 to from few nanometers to 100 nanometers of gaps.
Okay.
This is the range of the shifts.
Thank you again. Let's go to following. Now it's time to Ionel Ticinas from Technical University of Cluj-Napoca and talk about soft magnetic composite compact produced by spark plasma synthesis from pseudo core cell powered with monocrystalline core and unside freight cells. Ionel, the screen is yours.
Hello. Hello to everybody. Thank you to organizers for this workshop. I will present soft magnetic.
Could you share your screen, please?
Wait. Okay. Okay. Sorry. Okay, it's okay now.
Not yet.
Not yet.
This is okay. And now the full screen, please. Okay. Needs the time.
Full screen mode would be.
Yeah. Okay. Could you put the full screen mode, please?
Okay.
Yes. Okay. Down. You find the bottom, Ionel?
Yes, I try.
It's down. It's down on the right side. If you go down, can you find it? No. No. You have with the mouse go down and to the right side of the screen and close to. Okay. There. Perfect. Yeah.
It's good now. It's okay.
Not yet.
Not yet.
Needs the time. Now, finally. Okay.
It's okay now?
Yes, perfect. Okay, the screen is yours.
Okay, it's okay now?
Yes, You can
Okay,
start.
sorry for this problem. I will present submagnetic composite compacts produced by spatula sintering from pseudo-core powders and with nanocrystalline core and nano-sized ferrite shell. Background outline of my presentation consists in background and motivation, experimental details, results on discussions with two parts, pseudo-core powders and spatula sintering compacts, and followed by conclusions. So, why composite materials? Why soft magnetic? Why composite materials? The soft magnetic material consists in alloys, in magnetic alloys based on nickel and iron, and soft ferrites. Magnetic alloys have very good magnetic properties, magnetization and permeability, but because they are conductile materials, they can be used in AC application during the eddy current losses. So magnetic ferrites, because they are dielectric materials and they have a very, very high electrical resistivity, then they can be used up to megahertz in alternative current application, but they are very low magnetic properties. So this part is covered with classical magnetic materials. But nanocomposite ferrite, nanocomposite materials, we hope to cover this region of the application with medium magnetic properties and medium and high alternative current frequencies. You can see here the influence of the frequency on the hysteresis scars. With green, with red color is sintered magnetic alloy, and with red green color is magnetic composite. So, classical soft magnetic composites are composed by iron-based magnetic alloys, powders, which are covered with thin dielectric, organic and inorganic layer. The effects of this thin dielectric layer, the electrical resistance increase very much, but this is very good. But magnetization and the other magnetic properties decrease. It is not good. Our idea is to isolate magnetic particles by using a magnetic dielectric layer. You tried two ways for this. One is using pseudo-core particles, and the second to produce a magnetic alloy layer like raw metal at the base of two alloy particles. What means pseudo-core particles? You can see here a really core particle. The pseudo-core particle is formed by a magnetic core alloy and pseudo-continuously shell formed by very small particles of ferrite. Experimental details. You have prepared nanocrystalline nickel-3 iron permalloy and supermalloy powders by mechanical alloying. Use nickel and iron and molybdenum elemental particles. And for mechanical alloying, you use 2 mill to equipment, pulverizer 4 and pulverizer 6 for each ball mill, and milling time up to 10 hours. pseudo-core particles, preparation for nickel-3 iron and iron. We use nanocrystalline nickel-3 iron and iron powders. And we obtain some composition between permalloy particles and iron particles. This mixture was homogenization into volatile apparatus, and then were compaction and annealing and the post-annealing crushing and grinding. Pseudo like iron nickel alloys, permalloy, supermalloy, and ferrite, so magnetic ferrites like nickel ferrite, nickel zinc ferrite, nickel copper ferrite, and zinc ferrite. The powders, the mixture was homogenized, and then compaction, annealing, and the post-annealing crushing and grinding. Complex preparation, using these pseudo-kosher particles, you obtained many compacts by sparkler mass sintering, like this composition, core of iron and nickel iron alloy, and different type of ferrites. The powders and the compacts were characterized by particle size distribution, structural inlet diffraction using Equinox 300, and in situ high temperature inlet diffraction. Morphology composition was checked by scanning electron microscopy and ADX, and magnetic measurements, magnetization versus magnetic field, and induction versus magnetic field, and the other measurement, electrical resistivity. Some results concerning powders and compacts. You can see here the image of pseudo-kosher particle consists in a core of nickel-3 iron and layer of iron carbonyl. The powders were annealing, and you can see here the pseudo-kosher particles obtained after annealing at 600 Celsius degree. The same particles examined by ADX. You can see here the nanostructural particles is almost fully covered at the surface by a layer of iron, and you can see a good covering of iron with nickel particles. Pseudo-kosher particles obtained by iron particles and nickel ferrite. You can see here also the image and the analysis, and you have marked these iron nickel alloys and the border and the contact between iron particles and nickel ferrite. And by X-ray diffraction, we have evidence that the contact between iron particles and nickel ferrite, you obtain an interface of consisting in nickel iron mixed ferrite and phase like raw metal. Raw metal is the phase in nickel iron alloys with higher electrical resistivity. So some results concerning sparkler mass sintering compacts obtained by pseudo-kosher particles with core consisting nickel-3 iron or supermalloy, and a layer of very small particles of ferrite, nickel, zinc ferrite, copper ferrite, zinc ferrite. The results, the structure of the compacts consisting in permalloy particles, which are covered with a thin layer of nickel carbonyl. You can see here the layer of nickel carbonyl between you can see the nickel 3 iron clusters or particles in a network at the contact between iron permalloy particles and iron particles by annealing, we obtain a layer of raw metal, and we determine the thickness of this layer of raw metal between the particles and interface. This layer is up to 10 micrometers, and the thickness of the layer depends on sintering temperature and time temperature. The other sparse sintering compacts obtained by nickel 3 iron particles and nickel zinc mixed ferrite. The image, the macrostructure consisting in particles of permalloy and network, pseudo-continuous network of nickel zinc ferrite. The in situ X-ray, the in situ high temperature diffraction analysis between the range temperature range room temperature up to 900 Celsius degree show that no reaction between the initial phases. This is very good because if you obtain a reaction, you can have really composite compacts. The magnetic measurements was obtained by toroidal samples, and you can see toroidal samples from iron copper ferrite, and with here nano-size copper ferrite. X-ray diffractogram, X-ray diffractions of the sparse sintering compacts obtained by sintering at 500 Celsius degree during 2 minutes show that no reaction is observed between the starting phases. This is also very good. The microstructure of the sparse sintering compacts formed by a core of iron and a layer of copper ferrite. You can see the same scanning image of the microstructure of the compacts. Here, the analysis show that iron particles are covered by a thin layer of copper ferrite. You can see the ADX analysis. This ADX distribution maps of copper and oxygen is the same because they are composed of copper ferrite. So some magnetic properties. You can see these curves in DC current, and these curves in AC current obtained of the magnetic field 0.7 Tesla, and frequencies was between 50 Hertz, 500 Hertz, 1 kilohertz, 5 kilohertz, and 10 kilohertz. You can see here the magnetization, remanence induction, cohesive field, permeability, and a relative permeability of 75 for these conditions, and at 10 kilohertz frequency is encouraging. The resistivity, the electrical resistivity of the compacts is 110 to -4 on metals. This is 3-4 order of magnitude greater than than that of iron silicon alloys, which are the most resistive metallic alloys, metallic magnetic alloys. The last results is obtained for the sinter and consisting in permalloy particles surrounded with very small particles of zinc ferrite. You can see here electrical resistivity versus sinteric temperature. We obtain the electrical resistivity of the spark plasma sintered compacts with this composition, 10 to minus 2 on metals. That means 5 orders of magnitude greater than that of iron silicon alloys. These are the last our results. So, in conclusion, we obtain pseudo-core particles with core of nickel iron alloy and a shell of different soft magnetic ferrites. The core is composed by permalloy, supermalloy iron, and the shell consists in iron-based alloy or in soft magnetic ferrite layer. The permalloy, supermalloy metal composite complex has good magnetic properties. The electrical resistivity of the spark plasma sinter and composites compacts is with 4 or 5 order of magnitude larger than electrical resistivity of iron silicon alloys. Spark plasma sinter and compacts have a larger electrical resistivity as compared to the iron sinter and compacts or to the iron silicon sinter and compacts. Further investigation will be focused on the pseudo-core permalloy, supermalloy, and the manganese zinc ferrite and spark plasma sinter and compacts. And the other way is core shell, really core shell, iron and iron 3 oxygen 4 obtained by so followed by cold sintering. The magnetic materials group is here, and my collaborators for this presentation, Traian Marinca, Bogdan Neamciu, Florin Popa. And thank you for your attention.
Thank you very much, Lionel, for being on time. Now the talk is open to question. Any question, please? But I have a doubt about when you mentioned that SPS doesn't need maintenance, no? When you comparing the introduction with the milling method, you show in one slide that SPS doesn't require maintenance. Okay, we know that this is not completely. Can you comment this?
Sorry, please repeat.
Yes, in the introduction, in the first
introduction. So, we use spark plasma sintering because this method of sintering can use low temperature and short milling, short sintering time. So, in order to avoid the reaction between the particles. You have for some components you have a reaction, but for the other components you can see here we have no reaction and at lower sintering time and lower sintering temperature.
Okay.
And our aim is to avoid the reaction between the components, but also we use this interaction between the components for some composition in order to obtain an raw metal layer of interface. So depend. So this the reaction depends on the composite, depends on the sintering parameters, and depend also of our aims. When you have a reaction between the components, and you use this reaction between the components, is when you use two metallic alloys, two magnetic alloys particles, iron and permalloy. In this case, the reaction between the components is useful.
Okay, thank you very much, and thanks again, Lionel. Okay, let's move to next speaker. Is Maximilian Dors from Hochschule Darmstadt. Good morning, Maximilian.
Hello.
The screen is yours, please.
Okay, I will share my screen now.
Share your screen.
I should see my screen.
Okay, perfect. Okay, now it's yours.
Okay, perfect. Thank you for your introduction. I'm pleased to have the opportunity to give a presentation here. The title of my presentation, sorry, I have to switch my screen. Okay, now the title of my presentation is Parameter Study for Further Development of a Laser Diagnostic Method to Determination the Degree of Oxidation of Iron Particles in Reactive Flows. My name is Maximilian Dorst, and I work as a PhD student in the Laboratory for Optical Diagnostic and Renewable Energies at the University of Applied Science in Darmstadt. I used a laser diagnostic measurement method called laser-induced breakdown spectroscopy for this study, short LIBS. The first picture shows the beam path for the excitation laser. For the investigation of particles, the LIBS radiation is excited with this laser. The right picture shows the laser-induced plasma, which can be spectrally analyzed to measure the atomic composition of the particles. At the beginning, I would like to introduce briefly for motivation why it is interesting to determine the iron-oxygen ratio by means of the LIBS measurement techniques. In the diagram is now the electricity production of Germany in 2019 shown. If we now only look at the electricity production of renewable energies, here in yellow and green for solar and wind power, it is noticeable that fluctuations in the energy supply of winter months compared to summer months occur. For example, this month compared to this month. These long-term fluctuations must be introspected by storage facilities. Here, however, storage facilities with a long storage time and high storage capacities are needed if the renewable energy sources are to be further expanded. The Aragon plot diagram shows the different energy storage divided according to their storage time and their storage capacity. For short-term storage, for example, battery or water storage power plants are suitable. For the long-term storage times and high energy densities, only chemical in energy storage are usable. These chemical storage can be, for example, the currently much discussed hydrogen or ammonia, but also metals such as iron. And this is where the Clean Circles project comes in, which deals with the chemical energy storage of iron. I would like to present the project in the following. The idea is shown here in the sketch. To use the surplus electricity from renewable energy sources to reduce iron oxide to iron. This can be done by electrically produced hydrogen via electrochemical reduction or by electrochemical reduction. The iron powder obtained can be easily stored and burned in retrofit coal-fired power plants when energy is needed. The oxidation of the iron powder releases heat energy, which can be converted into electricity. From the oxidation, One received as emission only iron oxides particles, which can be reduced now again with energy surplus. In this way, a cycle is created in which energy can be stored separately in time and space. For the investigation of the physical and chemical processes during oxidation or thermochemical reduction, the LIBS measurement technique is to be further developed in order to determine the iron to oxygen ratio in particles. LIBS means, as already told, laser-induced breakdown spectroscopy. Here you can see two metal flames as an example for the energy release. The oxidation and reduction of iron particles takes place at very high temperatures. The challenge is to determine the atomic composition of the particles even during these processes. Other measurement methods quickly reach their limits at this wide temperature range. Further requirements for the measurement method is to achieve a non-intrusive high spatial and temporal resolution. As already mentioned, the LIBS measurement technique is used here. About my structure of my presentation. After the introduction and motivation, I will briefly explain how the LIBS measurement technique works. After that, I will tell something about the current measurement setup before I will present the first experimental results. Here are a few impressions shown. Single particles are fed over the lower flow apparatus. You can see the laser beam and the plasma generated by the energy input. As already mentioned, the measurement technique can also be used at very high temperatures, as shown here by the picture with the measurement on the flame. How does the LIBS measurement technique works? A focused laser pulse laser is used in the LIBS measurement technique. If there is a particle in the sample volume, it is melted by the energy input and converted into a plasma. At first, this emits a broad continuum radiation. At the end of the lifetime, sharp element-specific radiation can be detected at specific wavelengths. This allows conclusions to be drawn about the chemical substances in the plasma. Here's the beam path of the laser shown. The excitation can be done by a picosecond or a nanosecond pulse laser. The radiation emitted from the plasma is collected by a lens and fed via fiber into the spectrometer. Next, I want to answer the question, how is the defined feeding of individual particles into the sample volume achieved? For this purpose, a particle generator was developed according to the principle of a research group from Eindhoven. The schematic structure is shown here in the figure. We have two electrodes, and in the lower one is a regress to hold a particle bulk. The particle density can be adjusted by the distance between the two electrodes. Currently, we have around 10 millimeters, and the applied voltage, which we can set up to 10 kilovolts. The discharge of individual particles is done via a defined volume flow through a capillary tube. The main jet is surrounded by a co-flow. For the experiments with different oxygen concentrations, the container can be flushed beforehand. The excitation laser is located 10 millimeters above the outlet, and the measurements can be made along a 6 millimeter long 1D volume. Here's a CAD model of the particle generator shown. On the video on the left side, you can see the particle generator, and on the right side, you can see the lens. When I play the video, you will see the excitation laser and the generation of the plasma when a particle is in the sample volume at the same time. First, a parameter study is done to be able to analyze the signal in reactive flows later on. Here, the influence of different parameters on the signal is tested. The varied parameters are the excitation by two different lasers. Here, the excitation is done by a laser emitting pulses in the nanosecond range and by a laser emitting pulses in the picosecond range. Another parameter to be tested is the different atomic composition of the particles. Here, particles are fed whose element composition is known. For example, iron and various iron oxides particles. Furthermore, the influence of the surrounding gas phase is to be analyzed, since also surrounding gas phase is transferred into the plasma. This distorts the oxygen signal and must be corrected accordingly to determine the correct composition of the particle. The last parameter to be varied is the particle size. Here in this study are currently particles tested in the range of 1,000 to 40,000 nanometers. In further studies, it's also we will also analyze particles in the range from 100 to 1,000 nanometers. If someone here present can provide particles in this size range, I would be glad to hear from you. Let's move on to the first experimental results. First, a series of measurements with fixed parameters is recorded. The spectrometer is run freely with a recording time of 50 milliseconds. The laser runs at 10 Hertz. Thus, a lip spectrum is recorded once and a background image once. Since the entire radiation was recorded, the broadband continuous radiation in an early plasma formation process is also detected. This process is possible because the lip signal has a very short lifetime with respect to the 50 milliseconds. Here I would like to explain first how a series of measurements is evaluated. At first, an analysis is done which recorded spectra of the measurement series have delivered an evaluable signal, shown here in the graph. In the next step is evaluated what can be used as a background signal. In addition, it is shown here which spectra are not included in the evaluation because they have overexposed the spectrometer on the one hand, or on the other hand, they provided a too weak signal. In the last step, the spectra are averaged and corrected against the background. The spectra in the following slides shown such spectrums like this, which are averaged from a series of measurements. The wavelengths of interest can be considered for certain elements are taken from the literature. In the figure, the iron spectra from the LIPS iron spectra are shown from the NIST database. Here in the graph, we have plotted the wavelength over the intensity. In the figure on the right side, you can see the oxygen spectra from the NIST database. In the next slides, I will focus on the iron peaks at the wavelength at around 496 nanometers and at the oxygen peak at around 777 nanometers. First, I would like to talk about the results with the different lasers. Here you can see the lip spectrum from the nanosecond pulse laser. For better comparability, the spectra are integrally normalized here. One spectra for the iron and one is for iron oxide particles. It can be seen that the continuous radiation is...
Добре, добре.
Excuse me?
Там ли са твоите приятели или ти си само от студентите говоря?
Okay.
От студентите.
The broad background radiation overlays the lip spectra. However, the oxygen peak at 777 is still well visible. The figure with the spectra of the iron and iron oxide particles excited now by the picosecond laser shown a clear reduction of the continuous radiation, and now beside the oxygen peak, the iron lip spectra are also well visible here. If we now take a closer look at the spectra at around 496 nanometers, we can see the already told again. The iron spectra from the nanosecond pulse laser are only minimal indicated, where the iron spectra from the picosecond laser are clearly visible. So this is from the picosecond laser and here from the nanosecond laser. This is due to the fact that the picosecond laser pulse laser produces much less continuum radiation, which is superimposed on the lip spectra. Looking at the oxygen peak, we see that with a much shorter excitation via the picosecond laser, also much less surrounding gas phase is transferred into the plasma. This can be seen from the fact that the intensity of iron particles, which do not contain any oxygen per se, is significantly lower when excited with the picosecond pulse laser than excited with the nanosecond pulse laser. So if we compare here the peak from the yellow and the green one. If we stay with the already shown spectra and compare now only the iron and iron oxides particle, once excited here by the nanosecond pulse laser, we see here, as already mentioned, nothing available, which is due to the high continuous radiation. If we now compare the iron and iron oxides particle excited by the picosecond pulse laser, we see that they have about the same size here. If we now go to the oxygen peak at the nanosecond pulse laser, we see, as expected, an increase of the intensity of iron oxides particles because there is more oxygen in the plasma. With the picosecond laser, we see the same behavior. Knowing that the iron peaks have the similar magnitude, we can thus conclude that there is a higher oxygen content in the plasma for iron oxide particles like expected. Here are the results for different particle sizes of iron particles excited with the picosecond laser shown. Looking again at the iron peaks, we see that for larger particles, the intensity of the signal also increases. This is due to the fact that iron atoms are transferred into the plasma with larger particles. So later, also in reactive flows, the particle size can be analyzed by the Lipps signal. When looking at the oxygen peak, it can be seen that with increasing particle size, more surrounding gas phase is also transferred into the plasma. Finally, I would like to show the results for varying the time delay between the laser shot and the start of the recording. At a time at 1001.86, this is the first time, the start time of the recording responds directly to the time of the laser shot. If the time now becomes larger, so when we go up here, and thus the laser becomes larger, we see that the continuous radiation decreases and the Lipps radiation becomes clearer. Here the hole is shown enlarged again for the top here. Here you can see that the ratio of the Lipps radiation to the continuous radiation. The Lipps signal becomes more visible because less continuum radiation is recorded. Since these images were taken without an image intensifier, it can be also occur which are caused by triggering of the mini spectrometer. Therefore, in further experiments, this will be done again with an image intensifier. Due to the physical function, this image intensifier can be triggered much more precisely in terms of time and enable much shorter recording times than mechanical shutters. Finally, I would like to summarize the results once again. Many factors influencing the Lipps signal have been investigated. These are the excitation by laser by different pulse durations. Here, it is noticeable that with the picosecond laser, a clear reduction of the continuum radiation could be produced. Another advantage is the significantly reduced transfer of the surrounding gas phase into the plasma. Another investigated parameter is the particle size. Here it can be seen that the intensity of the Lipps signal increases with the diameter of the particles. This allows a determination of the particle size by Lipps. For different particles, iron and iron oxide particles, it was found out that the intensity ratio of iron Lips to oxygen Lips spectra allows a conclusion to be drawn here. Thus, the measurement technique can be used for the determination of the iron-oxygen ratio of particles. An influence of the measurement signal could also be determined by the parameter of the temporal delay of the laser shot in relation to the recording start. The delayed recording allows to reduce the temporarily first occurring continuum radiation, and thus makes the temporarily later occurring lip spectra more detectable. The laser next step is to install an image intensifier on the detection side and to use a better spectrometer. The advantage of the image intensifier is the more precise controlled, and therefore the time factor can be investigated more precisely. In addition to the parameter study is to be continued. Here, the influences of the surrounding gas phase is to be examined, but also the particle size is to be varied further. For this purpose, we need particles in the range of some 100 nanometers up to 1,000 nanometers. We would be pleased about contacts to groups which can provide iron particles or iron oxide particles in this range. Hereby, I would like to thank you for your attention, and if you have any question, just let me know.
Thank you very much, Maximilian, for this interesting talk. Now, the talk is open for a quick question, please. No. Yes. Yeah. There is a a question in the chat. Can you read or is
can you read it for me? Because I haven't opened the chat currently.
From Christina Graf. Is it possible to distinguish different iron oxides between magnetic and magnetic gamma Fe2O3, or between alpha Fe2O3, hematite and magnetic, okay. or only between iron and iron oxide?
Okay. There's you can only see the peak for iron and for oxygen. This is due to the fact that in the plasma the particles get atomized, and you only see the ratio from the iron to the oxygen, and therefore you can calculate back which iron oxide is or was in the particle.
Okay, thank you very much again, Maximilian. Let's move to the next talk. Is Enora Bullerman from Université de Technologie d'Artois. Again, sorry for my friend's accent. And Enora, the screen is yours. So, okay.
She's sharing
that. No.
Enora, is it possible to share just the next slide as well?
Okay, okay, but cannot hear you.
That's
yeah.
Is she muted?
Is it,
She's muted.
No me deja.
Ahora está abierta.
Okay, okay, perfect. We don't hear. Okay, the screen is.
Okay, thank you. Well, hello everyone. My name is Enora Vuillarmet, and I am a first-year PhD student at the University of Technology of Troyes in France. And today I'm going to tell you about Raman spectroscopy of silicon carbide using ultraviolet and visible light. So first, I will begin by a quick introduction to Raman spectroscopy. So in Raman spectroscopy, we are interested in the scattering light of the material. And we can see here that the vibrational energy of the atoms increases due to the absorption of the photons of the incident light, and to reach a more stable state, it releases a photon scattered. And in Raman scattering, the photon scattered has a different energy from the incident photon. So we can say that the energy of the scattered photons depends on the discrete vibrational energy of the material's atoms. In the case of a Raman spectrometer, we have a laser which hits the surface of the material, and then the scattered light is filtered, so only Raman scattering can go through and reach the detector. And because the photons of the Raman scattering have an energy which depends on the vibrational states of the atoms of the materials, we can say that the Raman spectrum is a fingerprint of the material. Raman spectroscopy can be used to characterize semiconductors because it's a contactless and non-destructive characterization method. Here you have a photo of the Raman spectrometer in our lab, and you can see that you just have to put the sample under the objectives of the microscope, like in a classic microscope. And the Raman spectrum that we obtain is dependent on the atomic vibration of the irradiated solid. And here you have an example of the Raman spectrum that we can have. And you can see that the band position gives us information about the structure of the material, and the width of the band gives us information about the crystallinity of the material, and so also information about the defects and doping of the material if it damages the crystallinity. The intensity of the peaks is proportional to the concentration of the photons on the detectors. And if we have a shift in the band position, it's because of the external perturbations of the materials like stress, deformation, pressure, or temperature. And here, in our case, we want to characterize silicon carbide. So why we want to characterize silicon carbide? It's because first, it's a wide bandgap semiconductor that it can be doped N or P. And so we can do electrical devices with that, like here, Schottky diodes. Also, silicon carbide has really strong chemical bonds. So it's thermally, chemically, and mechanically stable. And so it can be used to make devices which works in harsh environments. And silicon carbide is used in electronics, like for high voltage power devices, but also now in photonics and quantic, because with diamond, it's one material where we can create color centers within it for quantic applications. And so why we want to use Raman spectroscopy to characterize silicon carbide is because silicon carbide first has a lot of different crystalline structures. And as we can see here, the different polytypes of silicon carbide have a different band gap energy. And so the different polytypes have different electrical properties. And so we want to differentiate them, and we can do that by Raman spectroscopy. Also, like a lot of semiconductors, the electrical properties of silicon carbide can change with the defaults within the material, which can be induced by ionic implantation or doping. And with Raman spectroscopy, we can observe the damage of the crystallinity of a material due to these defaults. And finally, silicon carbide has also strong chemical bonds between its atoms, so it has a quite high Raman scattering efficiency. So first thing that we can do with Raman spectroscopy is to differentiate the polytypes of silicon carbide. Here you can see that we have two Raman spectra of different polytypes of silicon carbide, and the spectra have different peaks because the Raman peaks can be associated with the phonon modes of silicon carbide, and the phonon modes are the vibrational frequencies of the atoms, and they can be acoustic or optical. In the case of acoustic phonons, all the atoms go in the same direction under a light wave. But in the case of optical phonons, the negative atoms go in the opposite direction of the positive atoms under a light wave. We can also observe the doping of the material by Raman spectroscopy, and it's really important to ensure a good, because doping is crucial to ensure a good electrical conductivity of the material, and also the good operation of power devices depends on the doping of the material. Here you have an example of silicon carbide MOSFET. So you can see it's a multi-layer structures with layers with different doping. And so here you have the Raman spectra of a substrate of 4H silicon carbide with a high doping, and the Raman spectrum of thick epitaxial layer of 4H silicon carbide with a lower doping. And we can see the main difference is on the FLO peak, and that the high doping decreases the intensity of the Raman peak, but also shifts it to the right, and the width of the peak also increases. And one parameter you need to pay attention to when you want to characterize a semiconductor by Raman spectroscopy is the penetration depth of the light within the material, because it depends first of all, it depends on the wavelength that you use to characterize your material. Here you can see that the higher the wavelength is, the deeper you go in the material. And the penetration depth depends also on the absorption coefficient of silicon carbide. And so it can change according to the polytype and doping of silicon carbide. In our lab, we can use different wavelengths, and I use mostly one ultraviolet laser at 325 nanometers and two visible lasers at 405 nanometers and 542 nanometers. And so here you have one sample that we observed on two sides, the substrate side and the epitaxial layer side. And you can see that we don't have the same spectra because the substrate has a higher doping than the epitaxial layer. And by ultraviolet light, we observe only the epitaxial layer or only the substrate. So when you have multi-layer samples, it's really important to reflect to what wavelengths you will use to observe a layer you want. Then you can also play with the wavelengths and grating to change the resolution of the Raman spectrum. In the case of a wavelength, you can see here that when we increase the wavelength, the peaks are more intense, and also they are thinner. So you have a better resolution of the Raman spectrum by increasing the wavelength. But as we see before, with a high wavelength, you go deeper in the material, and so it's not really good if you have a multi-layer sample. You can also play on the grating to increase the resolution of the Raman spectrum. The grating is what you use to diffract the scattered light on the detector, which is a CCD chip. And if it has a high groove densities, you can see that the angle of diffraction increases, and so the resolution of the spectrum should increase too. And so here we study a sample with different grating grooves, and we see that with higher grating grooves, the peaks are slightly more intense and thinner compared to a low grating groove. Then we can also study the effect of the laser beam power and time of exposure on the Raman spectra. And we can see that when we increase the power of the laser beam, the intensity of the peak on the peaks increases too. And it's the same for the time of exposure. It's because when we increase these two parameters, we increase the number of scattered photons on the detectors. So it's normal that the intensity of the peaks increase. In the case of the time of exposure, the intensity is proportional to it. In conclusion, Raman spectroscopy depends on the vibrational modes of phonons in the solid. And we can identify silicon carbide polytypes and doping by Raman spectroscopy. The penetration depth of the laser beam depends on the wavelength and absorption coefficient of the solid. And the Raman spectrum can be adjusted by changing the laser power, time of exposure, wavelengths, and grating grooves. Thank you for your attention. Do you have any questions?
Thank you very much, Senora, first for being on time. And now the talk is open for question. Any question?
So, unless there is one in the chat, I would like to say anything in the chat.
No.
Okay, so Senora, thank you for your presentation. I'm curious about these different types of silicon carbide. How can you control their creation, or what does it depend on that you get one type or the other? These polytypes, is it possible to control their?
Yeah, it depends well on how you make your epitaxial growth. Because 4H, for example, is hexagonal, whereas 3C is cubic. And so often we use substrates with a certain polytypes, and then we do an epitaxial growth on this substrate. And to control the polytype of the substrate, well, it depends on the condition that you use to form the substrate. It can be the temperature, the pressure, or other parameters.
Okay, thank you. There is any other question? No, then thanks again, Lenora. So, let's move to the last talk, but not the least, of this 5th session is Michalis Koutinas from Cyprus University of Technology. So, Michalis, okay, you can. Perfect. Then the screen is yours.
Thank you very much for the very kind introduction. I wish I was actually with you today in physical presence, and I hope that in the future we'll have the opportunity to meet in person and discuss. My talk is very different to most of the talks that took place in this session, because my research is mainly focused on the production of biomaterials and on the exploitation of these biomaterials in bioprocessing. So this is the work we have been performing in the Environmental Bioprocessing Laboratory in the Department of Chemical Engineering of Cyprus University of Technology. So our main research interests are associated to biotechnological applications targeting the production of added value molecules like the biomaterials I'm going to show today. And we combine both systems engineering approaches like the development of mathematical models or advanced experimental techniques like molecular biology techniques in order to understand the underlying phenomena that take place in bioprocesses in the molecular level, in the cellular level, in the cell population level, in order to be able to improve these processes. So the main objective lies in the development of a circular bioeconomy. So human activity that has accelerated a lot over the past decades actually has increased the problem of waste accumulation and pollution accumulation. So we are trying to give a solution in accelerating this cycle in order to divert faster the waste that are currently accumulated back to the resources in this cycle. So the main effort, the main research effort in our lab is the development of biorefineries. Biorefineries are technologies that combine chemical methods and biological methods which are environmental friendly and hold the capacity in order to make this conversion, to exploit waste in order to produce resources. So the current practice is the oil refinery. So we are using non-renewable resources to produce commodities. In our research, we are trying to use bio-waste, like food waste, for example, in biorefineries to produce the same type of products, which are now more environmental friendly. And we are trying to do this both by producing products using microorganisms, using biological means, but also using ways of extracting molecules that have certain functionalities directly from this waste. So for example, we try to extract biopolymers that exist in waste, or molecules that have antioxidant properties, for example. So the first material I'm going to talk about is biochar, which is a highly carbonaceous material that is produced via pyrolysis, via thermal treatment of this type of waste. And current applications mainly focus on the use of these carbonaceous materials in agriculture as a fertilizer, or for the absorption of contaminants from wastewater, for example. We have developed a different route, which is the mobilization of the surface of biochar of biological agents, of cells in this instance, in order to enhance the performance of bioprocesses. So we have been developing these advanced biocatalysts that exploit this carbonaceous material in the production of bioethanol, in biofuel production. So the process that is producing bioethanol has a lot of problems related to the biocatalyst that is actually very sensitive to process conditions. So cells can be easily inhibited by the concentration of different molecules that exist in the process, like substrates, like the product, bioethanol itself can be inhibiting the biocatalyst, or process conditions like high temperatures. Now in the literature, most of the scientists are trying to tackle this problem by immobilizing cells inside alginate gel beads. Now, although this approach is increasing the production of bioethanol, the problem is that the properties of these alginate beads, the mechanical properties, are very poor. So when you introduce them in real processing conditions, they break very easily. So it's very, they are very easily destroyed. So we have been using biochar as a rigid carrier for cells. So the whole approach is that we collect different bio waste, we pyrolyze them, we transform them into a solid biochar, we attach cells on this material, and we perform the fermentation using this advanced biocatalyst. So forth, we have tested many different bio waste for the formation of biochar in different temperatures. So we have used a low pyrolysis temperature of 250 degrees and a higher one of 500 degrees. And we have analyzed the properties of biochar, like, for example, the specific surface area. We found out that that was higher at the higher temperature tested, and we reached up to 41.7 square meters of area per gram of the biomaterial. It is important to know that this was achieved without any activation. So this was not activated biochar that we produced in the end. It was the result of only pyrolysis. And each material had different chemical composition on its surface in terms of different elements. So perhaps not all of them are suitable for the growth of microorganisms. For example, this material here that was coming from seaweed residues, had a high chloride content, which could be inhibiting cells. Now, the physical characteristics showed that the biochars we produced were composed of both crystalline and amorphous structures. So when we use these different biochars that we produced via pyrolysis in ethanol fermentations, you can see here ethanol production in different experiments. In the second batch, we recycled all the cells that we harvested after the end of the first batch into a fresh experiment. And what we can see here is that 3 different materials shown with the 3 black lines had higher efficiencies as compared to the conventional process that did not use any biochar. So ethanol production was faster in these 3 experiments, but it was different when we used a different biochar each time. So different materials gave us different efficiencies in the process. Then we tested different microorganisms. So we tested 3 different yeast strains that are applied in bioethanol production. And we also showed that different strains have different efficiencies. So the material that could work very well with Saccharomyces cerevisiae, for example, did not give any advantage when we used a different strain. So we have looked at a lot of different conditions in this process. We have tested the recyclability in 6 different batches of this biocatalyst to see for how long the effect of enhancement is preserved. And we tested different stressive conditions like high temperatures, which could be very inhibitory for cells. 41 degrees is a highly stressive temperature for cells, and always the immobilized system performed higher biofuel production as compared to the control. We have tested different substrates to see whether this enhanced production is maintained when you use different substrates. We could even achieve triple final concentration of bioethanol using the mobilized system as compared to the control, using a substrate that we customly prepared in the lab using citrus peel waste as a resource. And we have been trying to identify whether metabolically the microorganism is protected when cells are attached on a biochar. So we monitored 3 genes, expression from 3 genes, which are activated when the cells are stressed, when they are under temperature stress. So we increase the temperature from 30, which is not which is a non-stressive temperature, from 30 degrees to 39 degrees, and compared the immobilized system to the control. So in the immobilized system, none of the 3 genes that correspond to stress expression were activated from the increase of temperature from 30 to 39 degrees. In the conventional process, we saw that all 3 genes were activated, meaning that the system was stressed. Now, what we are interested in this part of our work is to collaborate with a group that has the capacity and the expertise to be able to analyze the chemical units that are formed on the surface of biochar. So we want to investigate which is the mechanism that is actually providing this resistance, this metabolic resistance on the microorganism, and makes the process much more effective during the fermentation. So according to the literature, the surface of biochar, depending on the origin of biochar, depending on the bio-waste that you will use, and depending on pyrolysis temperature, the surface of biochar will contain different chemical units like carbonyls, for example, or ketones. And we would like to see how this chemical structure is changing over time during the fermentation in order to identify which is the mechanism that is responsible for this effect. Now, I'm going to talk about 2 polysaccharides that we produce in the lab. The first one is a fermentation product, and it's called bacterial cellulose. Bacterial cellulose, you can see here a picture of the way it looks like when we harvest it in the lab. It's actually a natural fiber that we produce microbially from bio-waste fermentation. And it's made of glucose units, a biopolymer made of glucose units. Now, this biomaterial has a lot of advanced applications in wood drenching, in drug delivery, in the development of scaffolds for tissue engineering applications, and as a food packaging material. Now, it has a lot of very useful properties. What I think is very important is the high purity. So although cellulose is a very abundant biopolymer in nature, because nearly the total of plant biomass on Earth contains cellulose, it's very difficult to harvest cellulose from plants in a pure form, because it's always mixed with other polymers contained in plant biomass. When you produce it microbially, you get it in a pure form. That's polysaccharide 1. The second polysaccharide is pectin. Pectin is a biopolymer that is composed of galacturonic acid units, and it's one of the main constituents of fruits. So waste that are associated, for example, to juice manufacturing have high quantities of pectin. And this is also a material that has very advanced applications, like you can use it in pharmacy, for example, to tackle high cholesterol levels. You can produce composites with bacterial cellulose using pectin. You can produce edible films, and it has a lot of applications in food manufacturing because of a lot of very useful properties. Now, we have been extracting this material from citrus peel waste. So citrus peel contains between 40 and 45% of its dry mass in pectin, and it also has valuable content in other carbohydrates and in other high added value products like carotenoids or polyphenols, for example. So we have in the past few years developed a process where we can actually extract pectin in a highly pure form from citrus peel waste. We can also extract essential oils. And to do that, we have developed an acid hydrolysis process that is assisted by sonication, by a physical process. So we extract these two products from the bio-waste, and the remaining sugars that exist, we use them for fermentations that produce bacterial cellulose. So we have developed in this process a design of experiments approach in order to maximize the amount of product that we get. The design of experiments approach resulted in the development of a statistical model that maximized the production yield of pectin. So we, according to our knowledge, this is the highest yield that has been ever extracted from citrus peel waste in pectin. We get 0.41 grams of pectin per gram of dry peel. So we have analyzed the properties of these two materials that we produce from the specific waste. The FTIR spectra of pectin isolated from different citrus waste, like Mandora, which is a typical traditional variety of citrus in Cyprus, and also from Valencia orange. We compared that with commercial pectin, and we found out that the profiles that we got were very similar. So it was a pure form of pectin we were isolating, and the bacterial cellulose we produce has the typical properties of bacterial cellulose, like the small crystallite size or high crystallinity. So in this project, we are looking for collaborations that could give us the opportunity to use the materials that we produce in the lab from bio-waste for advanced applications. So, for example, the bacterial cellulose we produce from glucose, we determined that it has very small openings of up to 5 micrometers. So this very dense-like structure could be potentially include also nanopores. So in that case, maybe this material is very useful to produce nanofiltration membranes. So we are looking for collaborations in order to find applications for these materials that we produce in the lab. So I would like at this stage to thank my group, industrial collaborators that we have previously worked with in the lab, and funding from both national and European resources. And I would like to thank all of you for your attention. Thank you very much.
Thank you very much, Michele, for your nice and interesting talk. And we are open for questions. Any question? Okay, I have one. Do you study the life cycle assessment of this kind of production of biomaterials, or there is something in the literature about this kind of study? Because I think that it is interesting to know what are the energy consumption in all these processes. Have you any comment about this?
This is something we don't do in the lab. We do it with collaborators in the projects that we work with. The life cycle assessment is a tool that you always have to use in order to assess whether your treatment approach is feasible from financial, from economic, and from an environmental point of view. And my answer is that parts of the process I have presented today, maybe not the whole biorefinery, let's say process flow sheet, could be beneficial from an economic point of view, but parts of this biorefinery could be cost effective. So, for example, to conclude, when we target the production of multiple products, maybe the process would be cost effective for the production of pectin. Maybe the process would not be cost effective for the production of bacterial cellulose. So my answer is that part of the biorefinery could be cost effective.
Okay, thank you very much. So let's thank Michalis and all the speakers of this session. Thank you. And now let's move to lunch because we are hungry. Thank you very much.
Yeah, maybe just a quick announcement because we're a bit delayed now, and there's been one of the talks of the last sessions won't take place. We will be starting at 2:30 instead of 2:20. Okay, so we will be delaying the start of the last session by 10 minutes. Thank you very much, and see you in a bit. Enjoy your lunch.
10 secunde. Ready, steady, go! Noile smoothies din fructe și legume, mixurile
Yes.
Ça, parce qu'on entend tout. Ok.
Ahora empiezo a compartir. Creo que se nos oye. Sí.
Okay, now we will continue with maybe the last session of the meeting. So I'm Jerome Blaine from EUTINN, and I'm very happy to be here and to have the opportunity to chair this session. So our first speaker will be Javier Cerrillo from the Universidad Politécnica de Cartagena, and the title of his contribution is Quantum Information with Josephson weak links, nanodiamonds, and trapped ions. Javier.
All right, thank you very much for the presentation. Let me share the screen very quickly. So I think it's working and you can see me too. So yeah, this is the last session of the workshop. And I have to say I'm very pleased at the level of the contributions so far. And I'm really looking forward to the contributions in this last session. It's been a great second workshop. We've shown for the second time that the European University of Technology is definitely very strong in the areas of nanoscience and nanotechnology. So this is great news for us, of course, and as well for the Alliance, right? It's a very big alliance, 8 universities across Europe, and it's a very good thing that there's such a strong research power in this direction. Yeah, so about what I wanted to say today, let's see if the computer responds. Okay. So as Jerome indicated, I'm going to be talking about quantum technologies, about the things that we do in our research group here at UPCT, at Universidad Politécnica de Cartagena. What we do is develop models and analysis tools for experiments in 3 broad ranges or areas in quantum technologies: in computation, in communications, and in sensing, right? And in different platforms. So here I mentioned 3: superconducting circuits, nanodiamonds, which is a topic that Christophe Couteau talked about on the first talk in this workshop. And also, although I'm not going to be talking so much about this topic, on trapped ions. This, for instance, is a picture of an experiment that is taking place not far from here in Granada. Granada is another really interesting city, beautiful, with a lot of heritage that is worth a visit. So if you're in the area again soon, I definitely recommend that. And what we have here is the first penning trap experiment for trapped ions in Spain. And the idea is to devote it to quantum sensing of and mass metrology, right? So the idea is trapping one sensing ion and having it sense the presence of a second ion, and through that being able to extract mass measurements and force measurements. This is not what I'm going to be talking about today. I'm going to be focusing on the topics of superconducting circuits and nanodiamonds. So this is a topic that we're very excited about. So as you know, big companies, Google, IBM, and more recently Amazon as well, are developing quantum computers, and they're basing this development on the technology of transmons, right, on Josephson junctions. But they're not working. We don't have quantum computers so far, and we have to improve the technology. And what we proposed here is to go into the topics of, into the direction of Josephson weak links. It's been a collaboration with Yale University, and we proposed the way in which we can use this new technology to host quantum information. And it was successful, and we recently published it in Science, so this is something that we're very proud about. And well, it's a new form of quantum technology, and I think it's useful to try to understand or at least have an intuition of what is the physics that hides behind, right? So let's look at these circuits. Here we have a layout of the sort of circuits that we mean by Josephson weak links. The idea is that you have a semiconducting loop, as you have, for instance, for Josephson junctions, right? But in this case, instead of having a very narrow junction and a very narrow gap in the loop, in the superconducting loop, what you have is a broad gap, and it's bridged by means of a nanowire, right? So this nanowire is usually semiconducting, right? And you have different sort of different physics arising in these architectures. Let's have a closer look at what is going on in this Josephson weak links. So you can think of these nanowires as conductors that have quantized conduction. So you have single electrons going through stochastically. And when a single electron reaches the interface with the superconductor, sorry? I guess you can all hear, right? Okay, let me stop this. I can mute some of the speakers. Okay. So let's go back to the screen. Yeah, so as I was saying, in these systems, you have single electrons tunneling stochastically. And when they reach the interface, they cannot just jump by themselves into the superconductor. They need to find a pair to form a Cooper pair. Now it's okay. And this means that they leave a hole behind, right? This is what is known as Andreev reflection. The Cooper pair goes on in the loop, the hole is reflected back, right? If you adjust phases and velocities correctly, then the Cooper pair and the hole meet and recombine again on the other end. And you have again your electron that travels again forward. So we have this Andreev reflection effect, which means an electron going into a semiconductor superconductor interface reflects a hole back, and the opposite happens with holes, they reflect electrons back. Okay, so in essence, what you have here is a cavity, a fermionic cavity, where you have modes arising, the quasi-particles, which are partly electrons, partly holes, right? This is what we call Andreev quasi-particles. These Andreev quasi-particles are localized in this nanowire. So first, because they're partly electron, partly hole, they're less susceptible to charge noise. And also they're more localized, so they're also less susceptible to flux noise. So they're extremely promising in terms of coherence times. The problem is the spin. I mean, they're fermionic particles, so they have spin 1/2. And this is where we would like to host the information, but it cannot be controlled directly. We have this degree of freedom, and with the controls that we have available, essentially electrodes, we cannot really operate directly and generate superposition states. So this was bad news initially, but we proposed to use third level techniques to be able to control this spin state. So our proposal, which was based in stirrup techniques, which some of you may be familiar with, made it possible indeed through a third level to generate these quantum superpositions. So we went from a situation that was not very good for just some weak links to the birth of a new quantum platform, and we're still developing these new ideas in this direction. Okay, the other topic that I wanted to talk about was nanodiamonds. Santiago will be speaking later in this session, and he will be telling you more about the topics that we're working on in the group. But yeah, what I wanted to do initially was to describe the defects that we're interested in. Christophe mentioned in particular silicon defects. We will be talking about nitrogen vacancy centers, where essentially in the diamond structure, in the carbon structure, you have two carbon atoms that are replaced by a nitrogen atom and a vacancy. And in this vacancy, you have two of the valence electrons of nitrogen that are very well trapped and isolated from the environment, and you can use them for quantum sensing. They're really they have really long coherence times, and they're only affected by some sort of magnetic noise mostly, right? So you can use this for magnetic sensing. And well, this is a representation of the ground state energy structure or energy levels as a function of external magnetic field, right? So in essence, you have two electrons. So either you have this magnetic number 0 situation where you have opposing magnetic moments, or you have the magnetic moments aligned of both spins in the electron, and this is energetically less favorable, which means that you have a very large gap, quadrupolar moment, as is known, which is very useful because it separates or it isolates this system strongly from thermal noise, for instance. So what is usually done in terms of quantum sensing is to address this transition here between the 0 level and the -1 level with microwave pulses. And in order to address this specific transition, you have to make sure that the MV center has a strong magnetic field around it, so that the Zeeman separation generated here is strong enough, right? But this is not always the case in experimental conditions. It's not always the situation that you have access to a strong magnetic field in the location of your MV center, right? So what we proposed was to study another kind of microwave addressing. This case, this addressing towards the zero field line. And even though it's not clear from this picture here, if you do this addressing, what you're actually doing is a Raman transition, in this 3 levels structure. And this Raman transition allows you to time in a different way your process so that you can achieve a high 2-level control of your system, even if you're talking actually to all 3 levels, right? So the details of the addressing and the timings are here in this PRL that we published last year. But I wanted to show essentially some of the more experimental, let's say, quantities that we improve with this new methodology. So for instance, let's look in terms of T2 times, right? As we show in these dashed lines, as the magnetic field, for instance, B, decreases, we see how this inability to distinguish the -1 and the +1 levels translates into a loss of coherence time of your NV center, right? With our methodology, with this effective Raman coupling that I mentioned, this addressing the zero field line, and these new timings of the process, we can, let's say, cure this problem and recover T2 times for this regime where we're in very small magnetic field. As you see in the plot, I have magnetic field and time. This time corresponds to the timing of the pulses, right? So in the picture that I had before, of course, even if you have a very large magnetic field with strong separation of both -1 and +1 states, if you send a very strong magnetic microwave pulse, so that your pulses are very short, you generate, for instance, pi-half pulses with a very short time. This means that you will be sending very strong pulses that will populate your +1 state, even if you have a strong separation, right? So there's this double effect, let's say. So you have these 2 regimes, low magnetic field or strong pulse driving. Both can be summarized into this quantity, the time of the pulse times the Zeeman splitting. So this new methodology is valid in both directions, right? On the right, you have let's say the equivalent plot for sensitivity, right? So how much error you make when you're trying to detect an external signal. And a similar thing occurs, right? When you go to very small magnetic fields or very strong pulses, you also have problems. The error increases by an order of magnitude, right? And with our methodology, it's possible to recover errors that are similar to the ones that you incur when you have large magnetic fields and good addressing of the 2-level system. Okay, so this is what I wanted to say. Thank you for your attention. These are the references. Something I wanted to mention is that this last method has been tested already in Ulm University. And you can see the archive preprint there, which will hopefully soon be published in Physical Review Applied. So you can also have a look at the results there. Thank you for your attention. These are also some references of other things that I didn't mention in this talk, and I'm ready for any questions that you may have.
Thank you, Javier. I don't know if we have questions, comments from the room. Questions? No? You know already all.
They're experts.
And maybe.
All right.
No. Yeah.
I have a question. My name is Traian Petrișor from Technical University of Cluj.
Hi, Petrișor.
In the case of superconducting loop, what kind of materials do you use? The superconducting loop is from conventional superconductors, or is from high TC superconductors?
In the experiment in Yale, they were using aluminum for the superconductor, and the semiconductor was indium arsenide. Those were the materials, but in principle, you can implement this. So, or Andreev quasi-particles should arise in any of these superconductor, semiconductor, superconductor interfaces, as long as the semiconductor can be considered one-dimensional.
And so your device works at low temperature, about below 1 K.
Yeah. There's really low temperatures. That's true. That problem we haven't solved yet, unfortunately.
And only for my curiosity, what is the dimension of the semiconducting wire?
So let me show you the picture again, where the specific numbers are.
Very useful.
The width is on the order of 10 nanometers, right? And the length, you can see here, so it's about 10 micrometers or so.
Okay. I saw.
All right. Thank you.
Yeah, I have just a short question.
Okay.
Because we know that superconductors are, how to say that, quite sensitive to the magnetic field. How the Andreev, what's the name? Reflection. Will be affected by magnetic field.
Yeah, so the flux is actually a parameter that we use for the control. Yeah, so it is quite stable, and the spectrum, let's say, that depends on the phase attached to the magnetic flux, is something that one has to control very carefully. But they can manage to do that, and it's well, experimentally accessible, definitely.
Okay. Thank you.
Okay, thank you.
Thank you.
I'm going to stop sharing.
Yeah. So now we will have the pleasure to listen George Angelov. I'm sorry for the pronunciation, which certainly is not reasonable. And I have not the title here, so sorry, but George is coming from the University of Sofia. And let's go. You can share your screen.
Thank you for the presentation. Now I'll try to share my screen. Okay.
Oh, perfect.
My name is George Angelov, or in Bulgarian we call it Georgi Angelov. So your pronunciation was quite right. I'm within the Technical University of Sofia. I'm currently a director of Information and Public Relations Directorate of the entire university. I'm also chair of Department of Microelectronics and vice head of ECAT laboratory, where we're doing integrated circuit design, device modeling, sensor design, and applications. Also, I'm running a laboratory in the Bulgarian high technology park called Sofia Tech Park, where we are doing root cause analysis of failures of integrated circuits and printed circuit boards. Within this laboratory, we are serving the industry mainly international companies with branches in Bulgaria and the region of the Balkans. And also me and our team are engaged in 2 long-term projects. They are EU funded for developing the so-called centers of excellence in the area of mechatronics and clean technologies. We have a laboratory for synthesis and applications of new materials in microelectronics devices. And also we have participation in another center of excellence where we are dealing with artificial intelligence and machine learning applications to automatization and manufacturing. The title is Factories of the Future. This is an EU initiative for maybe 10 years now, and we are dealing with this area. So this is the intro. Now let's proceed to the current topic. In this presentation, I will show you a portion of our work related to developing a sensor for measuring the pollution in the atmosphere, namely radicals of nitrogen and carbon oxide and dioxide radicals. The sensing device is based on a junctionless transistor. In the following slides, I will give a brief information about it. But in fact, the entire topic and the context is related to the well-known scaling of microelectronic devices dated back in the late 60s, 50 years now. You know that the Moore's law is describing and predicting the developments in microelectronics. And due to reaching the dimensions and the limit of this scaling, in fact, our previous speaker was, it was very interesting to see his works, but let's say these quantum applications, in fact, they arise from the fact that the mainstream industry will be soon reaching the end of the well-known state-of-the-art CMOS scaling. So now we have 2 approaches to circumvent these limits. One is to go in the direction so-called more Moore, and the other is more than Moore. These are definitions well known, but in fact, one is that we are trying to find solutions that will enable further development of the well-known CMOS scaling, and the other, called more than Moore, is related to diversification, such as quantum and other applications, also introduction of new materials and so on. In fact, our junctionless transistor that is in the core of our sensor is invented some 25 years ago by Jean-Pierre Coulange. And its principle of operation is very simple. In fact, it is correlated to the initial principle given by Lilienfeld in 1926, where he presented the so-called gated resistor. So here we have a nanowire, and in the middle of the nanowire, we have formed a gate. And between the gate and the nanowire, we have an isolator, the gate oxide. And in fact, this is a kind of nanowire transistor. It is junctionless because we don't have PN junctions here, in contrast to the conventional MOS transistor, where the source and the drain are with the opposite doping, usually N-type with the bulk of P-type. Here we have a nanowire. It is highly doped. And this construction, in fact, means that we have a normally on device. In fact, if we do not apply any voltage on the gate, the transistor is on. When we apply gate voltage, it cuts off. So this is again in contrast to the principle of the MOS transistor, where it is normally off. So the junctionless transistors, this configuration, is very prospective for sensor applications. And our core work for developing the sensor for measuring the pollution of the air is based on this device. I would like to say a few words that this is part of an EU-funded project, but this portion that I'm presenting now here, it is still not published. It is now submitted, and it is outside of the scope of the project. So, in fact, you know, every project has some milestones and work. In fact, these results are in addition to what is already supplied to the project, but it is inspired by this project. So I would like to stress that we don't not double the results and present them at more than one place. So our first paper that is cited here is dealing with modeling the device in COMSOL, and my presentation that I'm now sharing with you is based on modeling the device in Centaurus. Synopsys Centaurus, in fact, is one of the state-of-the-art tools for designing and simulating structures. In this case, semiconductor structures. Here is our simulation setup. In fact, we start from defining the geometry. In fact, in this morning, we had a regular meeting with the partners from this EU project that is developing the sensor. And in fact, the colleagues from Germany, they have already produced the prototypes. So now this paper that I'm presenting will be upgraded with comparing our model to real prototype experimental results. After defining the geometry, we go for extraction of parameters, then putting them in the model and simulating the transfer and output characteristics. And after that, we are again doing another calibration of the model for getting refined results. Just a second, excuse me. Okay, here is the workflow for developing the model in Centaurus. I will skip the details, but you can see that it is involved with a couple of files where we describe and define the geometry, also the materials with their characteristics such as doping and so on. I would like to stress once again that the nanowire is highly doped, and you will see later in the simulations that it is on the order of 10 to the 18th and 10 to the 19th atoms per cubic centimeter. Highly doped. Usually in most transistors is 10 to the 17th max. So we design and model the structure with all the files in the so-called S device. This is the Centaurus device editor. And we are in fact simulating and doing parametric analysis on areas. This is defined by the sizes, type of materials, doping level, and some distances. Here are some details of how the work process is related, but I will skip them. And this is the workbench, our workbench. In fact, it is very interesting tool. This Centaurus of Synopsys is very interesting tool. It gives a lot of options for to play with. Here is the main window. In fact, we have for each setup, for each device, we have at least start with two types P and N type of junction-less transistor. Then we made a lot of other combinations on different pairs and sizes. And in result, here is the window and what we can change. I will skip it. And finally, we are designing, and this is the design structure of the nanowire. Some of the dimensions are given here. You can know that we are in fact playing with a couple of orders. For instance, the length of the nanowire is changing between 3 microns to 10 microns. We also made simulations with 15 microns and 100 microns, but this is what we chosen to be optimal. Also, the gate length you see is in the range of 30 to 100 nanometers. This is also very important. You can see the scale in the middle, where is the gate. So the gate is a very small portion compared to the entire size of the nanowire. Here are the parameters that are input in the simulation. And having in mind that we would like to simulate the transfer output characteristics, here is the in-drain versus V-gate, drain current versus V-drain, and so on, standard simulations. We have produced a very thorough set of simulations with different dimensions and parameters, and we have analyzed them. I will here show you in a sequence not all, but let's say selected results in order to see how the dimensions and the parameters affect the performance of the device. And it's a trade-off. It's very important to see that, for instance, having a large doping gives us better current, but if you made it larger, the slope is getting worse. And for instance, we can hardly, because the leakage rises, we can hardly cut off the device. We could hardly stop the device. So it's a trade-off to find the dimensions that allow us an optimal design with optimal characteristics, because this transistor that we are currently designing, in order to come up with a sensor, the idea is to functionalize the upper surface of the gate. There, colleagues from other universities, partners with our project, are developing the, let's say, the chemistry, the layer that should be put there. And for us, it's very important to have sensitivity. That is, when the functionalized layer comes into interaction with the radicals, we should change of course, as in every sensor, we should change the magnetic and the field, in fact, the field, and this should trigger some impact on the gate, and in fact, we can sense it by the current flowing in the nanowire. So it is very important to select the right dimensions and parameters. Here I will go a bit faster because you got the idea. Here we in fact produced or simulated to the left transfer characteristics and to the right the output characteristics at different, you can see in the title, different setups, different dimensions. This is the p-type, they are opposite. And finally, in result, we optimized and tested different setups in order to determine the proper length of the nanowire and the proper doping level. And we here system classified the results. It's very important to maintain proper or close to the ideal subthreshold slope. In fact, you know that the ideal value is 67 millivolts per decade. In fact, we achieved close results playing with the parameters. Now, currently, as information is from today very fresh, the colleagues are still not achieving the prototype, the prototype is still not achieving the predicted by the simulation results, but it's pending topic that should be resolved in the coming months. So here is again a list of the how to say the outputs. The outputs of our work is that we come up with proper gate length, nanowire length, doping level, and based on this, the respective parametric analysis and critical analysis. Here is some key reference that was used in our work. Here are the, let's say, the foundation papers of Jean-Pierre Coulange, the inventor of the silicon junction transistor. And that was all from me. It will be a pleasure to hear your questions.
We were clapping, but then we were muted, unfortunately.
Thank you, George, for the presentation. I don't know if there is or there are questions in the room.
I was muted. You didn't hear me, really?
We were muted.
Yeah, we were muted.
Ah, you. Thank you.
Yeah, when we clapped,
I'm relieved because if I was
our
muted.
strong clapping for you. So
thank you. Thank you.
I could ask a question if there are.
Yeah, we have time.
Okay. So, I mean, I get it that you don't want quantum effects, but can you reproduce something, at least some, I don't know, modes within the nanowire or something with your simulation methods?
What do you mean modes of the nanowire?
Well, at least, I don't know, transfers due to transfer confinement. Something like that.
Aha. No, we are not getting so deep. I mean, the doping level is too high, so it's we don't have to account for, let's say, some losses or interference due to
okay.
Such as I mean confinements and other how to say, such problems and hitches are not accounted in the present simulations that are based, but still in the tool, in the Centaurus tool, yes, there is an option to account for such quantum, let's say, hampering effects.
Okay.
But here on the setup and the core, because I told you that the idea is to have a device that is at the core of the sensor. These are not still at this point, are not seen as, they could be neglected.
Okay. Yeah, I guess you're
in our next paper, when the prototype is ready, because some of our colleagues within this project, they are in Athens, in Greece, they in fact are doing the simulation from this bottom level, from reaching the quantum effects. We'll check if we account them, there will be some, how to say, visible results.
Okay. Thank you.
Thank you. So we can thank the speaker.
Thank you, it was a pleasure.
And the next one is for the
You can stop sharing, George, if you want.
Yeah.
Thank you. Thank you.
For me, the next one is M. Melianou, but I'm not sure that she will be here.
Yeah. She warned us that it would not be possible for her to present. I said I would ask if there was somebody taken up her place, but I guess it's not the case.
No. So the next one will be Prof. Gabor from the Technical University of Cluj-Napoca.
Can you hear me?
Yes.
Yeah,
My name is Elena Ștetco, and I will talk about our work on behalf of Professor Gabor. So let me share my screen.
Yeah, so.
Just a second.
Let's go.
Just a second, please. I don't know. Can you see my screen?
We cannot.
No.
Share screen. Now?
No.
No.
Not
No?
yet. Now it started. Now
Yes.
now we can see.
Oh, okay. Thank you so much for your feedback.
Okay, you can
go.
You can go ahead. Thank you.
Okay. So today I will talk about our work entitled Micromagnetic Modeling of a Spin Orbit Torque-Driven Memory Store. In my presentation, just a second, because I don't know. Okay. In my presentation, I will underline the types of memory stores: spin orbit torque memory store, spin orbit torque driven current induced domain wall motion in the presence of Dialoghinsky-Moria interaction, about device geometry, and about some conclusions at the final. So let's start my presentation with the memory store. The memory store or memory resistor is characterized by the relationship between the charge and the flux, was predicted as the fourth circuit element and described by Chua in 1971. Because the magnetic flux is the integration of voltage and the charge is the integration of current, the memory store is also defined as the ratio between voltage and current. The memoristic device is a solid state device whose electrical resistance is not constant, but depends on the history of the current that has previously passed through it. In other words, its resistance depends on how much electric charge and in which direction has flowed through the device. The difference between a memoristor and a resistor is that the memoristance of a memoristor is a function of charge which varies over time. Okay. The memoristors used so far are mainly focused on charge-based devices. They include field effects transistor devices, phase change devices, ion migration resistance change devices, and so on. Besides the charge-based devices, the spin-based memoristors are also proposed because of their improved endurance and energy efficiency. Recently, it was shown that current-induced spin orbit torques can be used to build devices demonstrating analog memoristic behavior. The spin orbit torque memoristic devices are highly energy efficient due to the relatively low currents needed for the magnetic texture manipulation and due to their non-volatility, unlike CMOS devices where significant amount of energy is spent in excess and leakage. The current-induced spin orbit torque arise from the spin Hall effect are usually evidenced in heavy metal ferromagnet bilayers, in which the ferromagnetic layer shows perpendicular magnetic anisotropy. The memoristic magnetic devices store the information in an analog manner in magnetic textures. Different types of spin orbit torque memoristors can be considered depending on the action of the spin orbit torque on the magnetic texture. Here, we address the spin orbit torque-driven memoristors in which the spin orbit torque moves a domain wall within the ferromagnetic layer. The key to the functionality of such a device lies in the possibility of controlling the motion of the domain wall. And the idea is how we can control the position of the domain wall of a perpendicular magnetized ferromagnetic field. Thus, we can imagine the memoristor in several ways. For example, we can measure the anomalous Hall effect resistance, and because it is proportional to the vertical component of the magnetization, it will depend on the position of the domain wall. Also, we can use such a ferromagnetic layer in a magnetic tunnel junction, and by changing the position of the domain wall in an analog manner, we can modify the resistance of the magnetic tunnel junction. For the memristor, we propose the following problems arise. How can we move the domain wall of a ferromagnetic layer with an electric current? How can we move a single type of domain wall? And last but not least, how can we create the domain wall inside the free ferromagnetic layer? And we will answer these questions through micromagnetic simulation performed in MUMAX. MUMAX is a general purpose micromagnetic simulation tool running on graphical processing units. It is designed for high performance computation and specifically targets large simulation. It solves the classical Landau-Lifshitz-Gilbert equation, taking into account the exchange interactions, the magnetostatic interactions, anisotropy interactions, thermal effects, and spin transfer torque. Periodic boundary condition can optionally be imposed. The purpose of the micromagnetic simulation is to find optimal parameters for the implementation of the memristor device we propose. The structure we use in this study is a typical platinum cobalt for which the material parameters were set accordingly. So the first problem is how can we move the magnetic domain wall with an electric current? As it was mentioned before, current-induced spin-orbit torque arise from the spin Hall effect are usually evidenced in heavy metal ferromagnet B layers, in which the ferromagnetic layer shows perpendicular magnetic anisotropy. Within the spin Hall effect picture, you can see here a charge current passing through a heavy metal with large spin orbit coupling will give rise to a spin current transverse in a transverse direction due to the asymmetric scattering of the spin up and spin down electrons. The spin current is represented by the two electrons with opposite spin, which moves in opposite direction. The spin current will enter into ferromagnetic layer and will give rise to two torques acting on the magnetization, the damping-like torque and the field-like torque. The damping-like torque is equivalent to a magnetic field, always perpendicular on the magnetization. This field will rotate the magnetization and will lead to the motion of the domain wall in the structure. The field-like torque is equivalent to a magnetic field transverse to the direction of the charge current and the spin current. These two terms were added in the Landau-Lifshitz-Gilbert equation, which describes the dynamics of the magnetization. In a ferromagnetic material with perpendicular magnetization, there are two types of domain walls, Néel domain walls and Bloch domain walls. Since in a nanowire, the thickness is much smaller than its width, the Bloch walls are energy favorable because inside the Bloch wall, the magnetization rotates away from the perpendicular direction. However, due to the symmetry of the torques that act on the magnetization, the Bloch walls will not move upon an application of an electric current. Fortunately, at the interface between a heavy metal and a ferromagnet, there is another interaction called the Haloginski-Moria interaction, which is an asymmetric exchange interaction, and if it is strong enough, it can change the configuration of the domain wall from Bloch into Néel. It was shown that the damping-like component of the spin orbit torque is efficient in moving the Néel domain walls. However, in the case where two consecutive domain walls are aligned along the same direction, since they feel the same effective field, they move in opposite directions. Since the DMI promotes a chiral domain wall, the in-plane magnetization inside the two consecutive domain walls are opposite to each other. They feel opposite effective fields, so the two domain walls will move in the same direction. To summarize, in this mechanism, the DMI provides the proper condition from the damping-like component of the spin orbit torque to be efficient for current-induced domain wall motion. So we have studied the current-induced domain wall motion in an ideal nanowire for different values of DMI constant and applying an in-plane magnetic field and a constant value of the charge current. We can see that when a current is applied at zero magnetic field, the velocity, and without DMI, the velocity of the domain wall is zero. In other words, the domain wall does not move because it is a blow wall. As we apply in-plane magnetic field, the magnetization inside the domain wall will begin to rotate perpendicular to the wall, so that the domain wall starts to have an L component, which increases with increasing the magnetic field. Thus, as we can see, the velocity increases, so the domain wall will move. The L component perpendicular to the wall direction occurs due to the DMI. Thus, if we consider the DMI, this component is essential in the study of the dynamics of the domain wall only by means of current, because as we can observe here, the magnetic domain wall moves even in the absence of the magnetic field. The velocity is different from zero. And this has an important technological implication because it can allow us to build field-free operating devices. For high DMI values, the velocity remains constant because the domain wall becomes perfectly net. In the graph from the right side, we represented the domain wall velocity as a function of the current, applied current for different DMI values. As expected, it can be observed that the velocity increases with increasing the DMI for a given current and saturates at higher current densities. The next question is how we can move a single type of magnetic domain wall. So in this way, we studied the domain wall velocity as a function of the current direction relative to the normal direction to the domain wall when applying a current at different angles relative to the axis of the nanowire. It can be observed that the velocity of up-down domain wall has a maximum, and at the same time, the velocity of the down-up domain wall decreases monotonously depending on the angle of the current. These results indicate that by choosing the optimal parameters such as current angle, current density, and DMI constant, we can be in the situation where we will have a maximum asymmetry between the velocities of the two types of domain walls. In fact, the current-induced domain wall motion is a motion through an effective field generated by the DMI. The fact that one domain wall has a certain velocity than the other one means that they field different effective fields. It is to be mentioned that all our simulations were performed for an ideal system. Sorry? Okay. For an ideal system in which the domain wall motion is also in the flow region. But in reality, however, due to the defects and disorders, the propagation of the domain wall can be in one of three regions: creep, depinning, and flow. Since there is always an asymmetry between in the motion of the two up-down, respectively down-up domain wall, what we propose is that by optimizing the geometry of the ferromagnetic layer and operating parameters, one type of domain wall to keep it in the flow region, and the other one to keep it in the creep region, so that we can get the motion of only one type of domain wall to the detriment of the other type. In order to get as close to reality as possible with micromagnetic simulation, we studied a polycrystalline nanowire by generating a granular structure using the Voronoi algorithm, in which each Voronoi cell represents a polycrystalline grain. After dividing the geometry, the material's parameters are varied locally. Thus, the value of the anisotropy constant is varied by 5% between grains. Respectively, the value of the exchange constant between grains by 5%. To understand the influence of the granular structure on domain wall motion, we first consider the dynamics in a system without disorder. The yellow curve represented in this graph represents the velocity of the domain wall as a function of the applied current for a system without disorder. It can be observed that the domain walls moves with a certain velocity for any current density. For a disordered system, as it can be seen, is that for high current densities where the domain wall is in the flow region, the domain wall motion in the granular structure is similar to the domain wall motion in the nanowire without disorders. The velocity is lower relative to the velocity corresponding to the ideal structure because the exchange constant between grains has been reduced. At lower currents, we can observe an abrupt decrease in the velocity, and at very low current densities, the domain wall remains pinned by the defect and no longer moves. So far, we have shown how we can move a domain wall and how we can move a single type of domain wall through an electric current. In other words, we have shown that if we apply current at different angles, the up-down domain wall has a higher velocity than the down-up domain wall. And the next question is how we can create the domain wall inside the free ferromagnetic layer. So a solution we propose is through a method by tailoring the geometry of the ferromagnetic layer. For example, by patterning the ferromagnetic layer with two narrow regions, these regions will become domain nucleation sites because they have lower thermal stability than the wider region. Moreover, the domain wall motion depends on the relative angle between the pulse current direction, which is set by the geometry of the patterned ferromagnetic layer relative to the current line. Thus, for a certain angle, it is possible to inhibit the motion of one domain wall type that can be formed during the nucleation. This means that for a given pulse current direction, only one type of domain wall, up-down, will propagate through the narrow region and enter in the rectangular stripe where the domain wall will propagate in the same direction as the pulse current. And by reversing the pulse current direction, the domain wall direction will also reverse. In order to validate this concept, micromagnetic simulations were performed for a structure in which the ferromagnetic layer was modeled with a narrow region, the tip of which representing the nucleation site of the domain walls. Initially, we have considered a non-disorder system or a system free of disorders. Current of a certain value is applied to the sample on the stripe direction, and we can observe that the two domain walls up and down move with a certain velocity different for the two types of domain in the pulse current direction. If we apply a current pulse in the opposite direction, the domain walls move in the opposite direction. But the domain wall motion is not perfectly reversible due to the asymmetry of the motion between the two types of domain walls. For a disordered system, as expected, it can be seen that one domain wall up-down remains thin and does not move, and the other one propagates in the rectangular region of the structure with a certain velocity in the direction that the current pulse is applied. Also, similar to the non-disordered system, if the current pulse is reversed, the domain wall propagation is also reversed. In conclusion, we propose a spin-orbit torque memristor for its improved endurance and energy efficiency. We have shown the influence of the spin current on the magnetization and how we can control the position of the domain wall. We have shown the influence on material disorders on the dynamics of the domain wall and how we can move a single type of domain wall. And we have shown that by tailoring the geometry of the ferromagnetic layer, we can obtain field-free operating devices. Thank you very much for your attention.
We have time for one short question, maybe. There's a question here or a question in the room. I have a very naive question. So, how is measured the velocity of the walls?
It is measured through micromagnetic simulation.
Okay. And then in the experimental way, in case of?
In the next step, we will measure the velocity of the domain wall in our laboratory. At this point, we only perform micromagnetic simulations through MUMAX.
Okay. So, thank you. And
thank you.
So the next speaker is Santiago Oviedo Casado de la Universidad Politécnica de Cartagena, and he will speak about super resolution in nano NMR.
Lo comparto todo y luego tú. Esto. Se pasa con la flecha.
So, hi everybody. It befalls to me the honor to close the meeting. So I just would like to say thank you to everybody for a very nice talk. I've learned quite a lot when it's been 2 intense days, and also thank you to the organizers because I know it's been stressful. I've seen them. I've seen Javi. So yeah, I wanted to tell you. Well, I'm part-time here in Cartagena. That's true, but I'm also part-time in the Hebrew University of Jerusalem. And so today I wanted to discuss a few of the results we've been working in regarding the program of Nano NMR. So, well, yesterday you heard Susu talking about biomedical applications of quantum sensing. This is the other platform, or I don't know if it's the rival platform that can be used for it. So before starting with Nano NMR, let me begin with a gentle introduction, which is what is nuclear magnetic resonance. Maybe probably for all of you, it's just a reminder, but I think it's useful. So in nuclear magnetic resonance, we have a big collection of nuclei, and room temperature, they are randomly oriented, and this means there is no net magnetization. So if we apply a typically quite strong magnetic field, some of the nuclei, they orient in the direction of the magnetic field, they start precessing, so there's a net magnetization, they start precessing. This precession generates an oscillating magnetic field. This oscillating magnetic field generates a electric magnetic field on a coil, and then we can detect this electric field, measure it, and infer properties about the nuclei that are in the sample. So that's very briefly what nuclear magnetic resonance is. So to summarize it, is basically this thing. We have a sample and a coil and some other things. But the big problem, or one of the big problems that NMR has, is that, well, basically you usually need a apparatus the size of typically a room, and it's quite expensive. It's not very environmentally friendly. You need either very low temperatures for the high magnetic fields and so on. So even though I'm not claiming, I mean, it's been a very successful technique both in science and in medicine, we would like to try to make it easier. And there's been proposals just focusing on trying to reduce the size of the apparatus involved in NMR. But even though they've managed to reduce it, they haven't been very successful. And this seems like to be a dead end. Like they won't get further, and they are not what they were expecting them to be. So I told you what NMR is, and we want to detect, basically it's based on detecting magnetic fields, and the ultimate magnetic field detector, or the smallest thing we can imagine as a magnetic field detector, that would be a spin, single spin. And that's what nano NMR is based on. So typically for nuclear magnetic resonance, the classical one, you need of the order of 10 to the 13 spins to generate a sample and then to measure and so on. And we would like to reduce it to one spin measuring another spin. Basically, taking how I summarized NMR before, we now have that the sample is reduced to whatever molecule we are interested in, and we take the coil and everything and all the apparatus and everything and reduce it to just this spin. And I had these slides because they usually are in these presentations, but the nitrogen package accepted diamond has been already introduced to you. So I won't focus again, I won't describe it again, just say that, as was mentioned, it is the ideal platform for the nano NMR scheme because it has very long coherence times at room temperature. One of the things that we would like to have is rather than having to cool down the samples a lot to then apply the magnetic field and polarize them and so on, we would like to perform the experiments directly at room temperature because we would like to work with biological samples, which you don't want to cool down generally. And so this is the level structure and so on. And here, rather than the 3-level techniques that were introduced before, I'll just focus on producing the MV-centered, a simple 2-level system. Very easily to control with, as was said, microwaves and some lasers and so on. But yeah, we know how to do that with very high fidelities. So in the working with the MV as a magnetometer to detect magnetic fields of samples, what is typically done is you have some MV which is close to the surface of a diamond, artificially made diamond. This is not, you won't be really rich having those. And then you put a sample, a small sample, drop of whatever fluid you want to measure on top of the surface, and then the diamond generates or has an interaction region, which is typically a hemisphere above the surface of the diamond, where there are a few nuclei. And then these nuclei, because it's a small number, you have a statistical polarization, so you don't have to use, and that's another very good thing, you don't have to use high magnetic fields to polarize the sample. You have the polarization by default because of the small number. And this generates a magnetic field, which is detected by the MV. And we detect it through changes on the probability of the MV step. So that's how it's done in the experiment. But the question is, well, we have to know how to do the experiments properly. That's one part of in which we've been focusing. And the other one is you have to take some care about the post-processing. So typically, in these experiments, because you are measuring a quantum state, you have a string of zeros and ones, it's a digital signal. And if you do Fourier transform, well, you might detect some spectral line, which gives you some information. If you do some more complicated signal analysis, you might see that your Fourier line has more features. And then what we would like to is to have, and this is the super resolution part of the title of the talk, we would like to have super signal analysis in which we can resolve basically all features that are hiding in our signal. Then we can access any kind of sample. So those are the two things we've been working on. And in nano NMR, because we are working with liquid samples, the main problem, and because we have this hemisphere region, which is quite small and so on, the main problem is that the molecules within the sample start diffusing, they get out of the region, and the correlations are lost, the magnetic field decays, and we don't see any signal. And this is reflected on the spectrum that we want to measure as a broadening of the spectral lines. And that's the main source of noise. So that means the statistical polarization tends to disappear with time. And and for now, I'm going to assume that the coherence time of the MV of the probe is shorter than the coherence time of the signal. If we have just one spectral line, then there is no problem on being able to measure it. Basically, and this is classical optics, you just need to perform as many measurements as needed, and then you can estimate it, where the frequency is. But if you have too close spectral lines, then you run into a problem, because as they get close together, they overlap, and they are seen as just a single spectral line, which you cannot say, okay, I have two here. And you can study that by calculating the uncertainty inherent to this probability of measuring the MV center state. And you see that it diverges as the frequencies get close. So we would like to solve this, find a way of being able to resolve arbitrarily close spectral lines. And then the intuition that's behind this should have been a gift, but in PDFs you cannot do that. So the intuition is that, okay, I have two spectral lines, or two things in 2 dimensions, and in 2 dimensions, as they get close, they are basically the same, so you cannot say I got two things. But if you choose an extra dimension, in this case, in the picture is the color, then it doesn't matter that they get close enough, because you can still distinguish them through the 3rd dimension, which is different. And so we translated this problem into the MV thing and the nano NMR by considering that, so this is the relevant Hamiltonian that governs the interaction between the magnetic field and the external signal, by saying or seeing that the parameters of the interaction are noise due to the diffusion, so the inherent noise that the problem has, and this means these parameters change. And we can use the change of these parameters as our 3rd dimension. And we were able to demonstrate that rather than, if you remember the previous uncertainty, it diverged as the frequencies got closed. Now we demonstrated that, again, it only depends on the amount of measurements that you need to perform to distinguish these 2 frequencies. So we've mapped the problem of resolving 2 close frequencies to that of estimating just one single frequency. And you not only need this post-processing, you also need a suitable measurement protocol. In this case, it means that you have to be sensitive somehow to this noise because you want to use it. And for that, they developed in Ulm and some other groups a protocol in which you measure sequentially, controlling the time between measurements very carefully, and recording it, and then you can reconstruct this time, and this gives you information about the oscillations, the phase, and so on of the signal, and information about the noise. And then you perform Bayesian analysis, and we demonstrated experimentally. So here the blue line, here that's the Fourier transform of the signal obtained from the NB, and the histogram represents the Bayesian analysis that we could distinguish two close frequencies which otherwise would have seen as a single line had we done just Fourier transform. So that's mostly about the post-processing, and I told you that I had been thinking on signal whose coherence time is longer than the NB, therefore you can measure, say, as much as you want, but what happens in the other limit, say, if your signal decays faster than the coherence time of the NB, so you cannot perform any number of measurements. Then, in principle, you had a problem. So to solve that, we had to go into the very details of how the signal decays in a statistical polarization when you measure with NBs. And here the typical assumption, and this comes, well, typically because it comes from NMR, and there the signals, if they decay exponentially, so everybody assumed, like, okay, in nano NMR, they will decay exponentially as well. But it turns out that if you consider that the interaction between the nuclei and the NB center is dipole-dipole interaction, then things get a bit, they are a bit different, and the decay is not exponential, or is only approximately exponential at very short times, but at long times, it's polynomial. This is due to the dipole-dipole interaction and can be calculated, and it gives you this horrible expression, but can be understood as simply this decay. And then we can, for such a decay, calculate again what would be the uncertainty of our measurement. And for the Lorentzian assumption, which is if we have exponential decay, the spectral lines would be Lorentzian. Then, as you see, we run into the problem of divergence when frequencies get close. But for the power law, in particular with this is exponent dependent, it again is a problem of how many measurements to perform. So using QDyne again, and being sensitive enough to detect and to measure the correlation function at these later times, then we can gather much more information from the signal and be able to resolve frequencies. And the intuition here behind it is, you remember the picture from before, as the lines get close, they overlap. But if this is only if the lines are Lorentzian. If they are not Lorentzian, if they decay as a power law, they are sharp peaked, and even if they get close, you can still distinguish the peaks because they subtract each other. So the difference remains there. So we simulated it with we did molecular dynamics of the statistical polarization, and we input some real frequencies, and you can see that not only the width of the lines is the same as if we were using just one frequency, while you wouldn't see anything for Lorentzian decay. You can distinguish 3 lines. Which, this is an experiment they did with high magnetic field. We did the simulations assuming that you don't polarize the sample. And this was published in 2020, and since then, they've been working in Germany on performing the experiment, which is not simple because you have to measure the correlation function at a very long time, and it's noisy and it's complicated. But we've been all this fall working on it, and we are close to be able to submit it, that indeed we've detected experimentally this long tail decay, this power law decay for the first time, and also that it can be used to resolve frequencies which otherwise, like you see here, if the decay were exponential, you wouldn't be able to resolve. And this tells, because so not only the exponential decay paradigm is quite extended and seems like it's not entirely correct, although for short times it provides a very accurate description as has been used very successfully, but also that typically The methods they use when they analyze the signals, it's basically people rely on Fourier transform. But if you use Bayesian analysis or other statistical, more sophisticated statistical techniques, you can see that the width of the spectral lines that you can get, it's much smaller. So this is also a kind of trying to say to the people, forget about the old classical methods. It might be a bit more complicated, but it's worth it because it allows you to implement the program of nano NMR. So with that, I conclude that's the thing. So we demonstrated that EUTINN is in principle the best protocol you would want to use rather than simpler protocols as power spectrum, and that you have to take real care about how you post-process the signal and all the futures. Now that we've demonstrated that you can detect signals from they used some oil, so from relevant samples. Next step would be to apply it to some medical or something that is really interesting for not only for the physical community but for other communities. And so this is the people I've been working with. Top row, people from Ulm mainly, many evenings discussing, and low row, people from Jerusalem, with which I've been doing the theory. And yeah, thank you. That's all.
So questions? I have a very naive question.
Maybe not. Naive.
No, in that case, definitively naive. All the post-processing you made is long in time?
So the Bayesian analysis takes typically between days and weeks of computer time, yes. That's why we couldn't apply it really to when the signal decays faster than the coherence time of DMB, because then there are too many parameters and it becomes too big. That's how we came to the other long decay tail. But for the long decay tail, it's very fast. Then you don't have to do much I mean, it's a matter of minutes to analyze this.
Yeah.
But yeah, the Bayesian analysis that's takes a long time.
Okay, yeah, because it could be a limitation in terms of
yeah, it is.
Theoretical application,
medical
thing. Yeah. So maybe I don't know if there is question in the room. I don't know if it's possible to see. Some questions?
Stop sharing because otherwise you can.
Yeah, it becomes here. No, okay. I think there are no questions.
No questions in the virtual room and in the other questions. So maybe it's time to thank the speaker, all the speakers of this session, and maybe Javier and Christophe, if you want to, or Javier, if you want to say something in order to close this very nice meeting.
Well, thank you very much to all the speakers. It's been a pleasure, an honor to be able to organize this workshop. As I said before, it shows how strong the European University of Technology is in nanoscience and nanotechnology. And this is something that we should be very proud of and work strong so as to build up not only with all the workshops that we have done, but also with other activities in the future. So yeah, I don't know if Christophe wants to say something additional.
No, thank you. I want to thank you for the organization of this. It was very nice. Then no, let's meet for the third one at some point soon, right?
Exactly. We now is the moment to start thinking about the third one, about location and moment. We'll probably have a meeting soon with the point of contact And we'll keep informing about the advances in the future. So thank you very much. Thank you, the speakers. Thank you, Santiago, and thank you, everybody.
Thank you.
Okay, so everybody have a nice trip back home in your locations. We'll go for a walk in Cartagena, so I'm sorry you cannot join, but we'll meet hopefully in the next one physically. Bye.
Bye.
Thank you.